Hello, Avas is audible?
Yes, sir.
Okay, good.
Teacher.
What was the echo in the morning?
I think you were using this two. You are logging in two devices. That's why I think it was
And I
going.
am on only one.
Then I don't know why. Because when you started, it was fine, but
Yeah,
later.
I have only one device. I am not just Google
Or
Talk.
maybe if you are using a speaker, then it happens sometime.
Oh, I am going to use this computer speaker, nothing else.
So now it is fine. Currently, it is okay.
All right. So I am doing this online class through this only.
Yeah, okay.
I think Moni is there.
Yes, yes.
Hello, Moni, how are you? She is not around, I guess.
Hello,
Yeah, Moni, how are you?
I'm fine, sir. How are you?
Good. Everything is fine?
Yes, sir.
All right. Is it cold there?
Sorry, sir.
Cold there, or how the weather?
Yeah, yeah, a little bit cold.
I see. All right.
What about there?
Yeah, it's a little bit cold, not much.
Okay.
Weather is good. Yeah. What is the time?
Time is 11 here.
11 o'clock.
Yeah,
I see. So it's European time.
yeah.
Are you teaching something or what?
Sorry, sir.
Are you teaching something or?
No. Here there is no teaching. Like,
All right. Good. That is good then.
so what you are teaching this semester? Like,
No, I was teaching over. I was teaching commutative algebra.
oh, next semester.
Now this semester it got over. 2 weeks last week or 2 weeks before. Last week
Yeah.
it got
Okay.
over.
And
Yeah.
next semester, what you are planning to
Next,
teach?
I don't know. No plan yet. No meeting yet. No, not
Okay.
means you have not finalized. Yes, because next semester will start in sometime in April or March last week.
Oh,
Yeah. So in the same place with Orbin or different place?
no, we stay in the same place.
University are same.
No. He is in the Huji. Sorry,
Oh,
Hebrew University.
that's different university than
Yeah,
your Bar
yeah.
Ilan something like that. No.
Yeah. Mine is Bar Ilan,
I
and
see.
he is in Hebrew.
Okay. Uh, is far from the university or Ojitara
Yeah, I think 60 kilometers from here.
or not very far?
No,
Okay, that is good.
by bus it takes around 1.5 hours.
All right. Okay, let's see. We're going to start our soon or 2:26. Yeah. Okay. See you then.
Yeah. Okay.
Yeah.
Sir.
Yeah. Yeah.
Bye.
Yeah, so we can start now. So, welcome to the afternoon session of this conference. First speaker for this session is Professor Vrindavan Sahu from NISER Bhubaneswar. So, he has completed his PhD from HRI Allahabad. Then he did postdoc from University College Dublin, Ireland. And he works in the area of number theory, more particularly some automorphic forms like modular form, Siegel modular form, and Jacobi forms. So today is going to talk about ranking point bracket on Jacobi forms of several variable and special value of certain digital series. So please I request Sausa to share his slide and present his talk.
Okay, thank you very much, Abbas, for invitation and giving me opportunity to talk here. So I'd like to share the screen now. Screen is visible now?
Yes, sir. So maybe
Yeah.
you can, yes,
I
you
do
can go
the
full screen mode.
visible, yes?
Yes, yes, fine, perfectly
Okay.
fine.
So I'm going to speak something or ranking point bracket on Jacobi forms of several variable and special values of certain declared series. And this is mostly joint work with Avas Kumar Jha. So this kind of talk I've given last 3-4 years, but I'm giving it like a survey talk kind of thing. So let's start. So this is my outline of the talk. Having this transformation property of the form if zeroth coefficient is 0. All right. So now we give these notations. Mk be the space of modular form weight k for gamma. Gamma is set to z. And sk be the space of cos form of weight k for gamma. And this the space of cos form weight k is a Hilbert space with respect to the Peterson unit product defined like this. And here this gamma, this f is a fundamental domain for this action of gamma on a Vara plane. Now we define a declared series of Rankin-Selberg type. So f is a cosmos weight k, g is a cosmos weight l, f has Fourier coefficient ans, g has Fourier coefficient bn. Then for every integer, every positive integer n, we define this declared series. So this is shift on n. Given a n, we have a shift on am plus n and bm bar. So this is the usual Rankin-Selberg type declared series. And using the bounds of the Fourier coefficients, we can see that this this declared series converges absolutely for L less bigger than k plus L by 2. And this has also meromorphic continuation to C, that is the result of Anton Good in 1983 regarding this. All right, now I'm recalling a theorem of Cohen appeared in 1991. What he said basically that if you take an integer k bigger than 2, and an integer and g is a cos form weight L with Fourier coefficient Bm, and you take another cos form with weight k plus L with Fourier coefficient Am, then you take the functions defined by these Fourier coefficients, namely the nth Fourier coefficient is 1 times the spatial values of this Rankin-Selberg type declared series at the point k plus L minus 1. This is the Fourier coefficients we are going to talk about. So this TFG star defined like this, and this really say that this is a cos form weight k for gamma. So there is something further. This maybe I'm putting a TG star here. So TG star is basically, we consider this TG, given a G, we fix a G now, and we have a map from SK to SK plus L, defined by H goes to GH. So we know the product of two modular form, again modular form, and the weight get added. So H goes to GH for a fixed G. This is a map from SK to SK plus L. So this is going to be linear maps, and we are talking about the adjoint. And the TG star, the modular form defined here is nothing but the adjoint of this particular map. That's how we're going to relate it. All right. So let me give a sketch of this proof, because we are going to use the similar kind of argument in the next few theorems on different set of. So we have this TG, SK to SK plus L is a linear maps of finite dimensional vector spaces. So there is a unique adjoint map TG star from SK plus L to SK defined by this inner product. So let PKN be the nth Poincare series in SK. Sorry. Oh, there is something. Yeah. Yeah, so this is the nth Poincare series having these characterizations. Namely, we take the inner product of H, any cos from H with PKN, then up to some constant. This looks like the nth Fourier coefficient of H. All right. So what we do is that we want to find this coefficient of we want to find the nth coefficient of TG star F. So this is basically the inner product with TG star, this characterization of Poincare series. And if you take the adjoint to the other side, so you get F of TG PKN. And by definition, TG PKN is the G times PKN, the nth Poincare series. And this is the definition of the inner product. And all right, so now we are writing this capital FZ to be FZ GZ bar to the power Y to the power L. So that's why I replace here this first one to be like that. And now this function's capital FZ transforms like a modular from weight K under the action of gamma. So, and we do this standard Rankine unfolding argument, and we take this sum inside and integrations, and interchange these sum and integrations, and we have to finally compute this A, F, and Y. And that's what we compute this. And it turned out that if you solve these integrations using a particular fundamental domain, then you get this particular special values of the Rankine-Selberg L functions at these values. All right. So this is how the proof goes. Then there are several generations to this theorem in 1996 by Lee for Gilbert modular forms, Gilbert modular forms by Wang, and there are generation by Jacobi forms. I'm going to speak this on Jacobi forms after a few minutes. Yes. So let's wait for Jacobi forms. So there are another generalizations to this. So basically using this Rankine-Cohen bracket. So let me just formally define what do you mean by Rankine-Cohen bracket. So if F is a modular from weight K, then you take the derivative. Here D means 1 by 2 pi D by dz. And we see that the derivative of F satisfies this particular relations. Basically, D of Fz plus B by Cz plus D, Cz plus D by K plus 2. Earlier the modular form F was modular form weight K. Now this becomes weight K plus 2. And there is a term that does not allow this to be modular because this Kc term is there. So unless K equal to 0, we don't get a modular forms. So there are this kind of error term is there. So the thing there, how to find modular form using this differential operator. And the result of Rankine, he studied polynomials in 1950s. He studied polynomial in n plus 1 variable so that you can construct modular forms using this F, df, dnf, the nth derivative, etc. So you can write in terms of polynomial of derivatives of n. For example, one of the example is here, kf d square f minus k plus 1 times df square is a modular form weight 2k plus 4. Okay, then another one looking at the symmetry property, one can see that if f is a modular form weight k and g is a modular form weight l, then these particular combinations kf dg and derivative of g minus lg derivative of f, basically you kill this error term in the final things. So this is modular form weight k plus l plus 2. All right. So using this similar idea, Cohen in 1997, he proved the following. You take a modular form of weight k, you take a modular form g, modular form weight l, then you take the nth Rankine-Cohen bracket of f and g defined by this fg bracket n. This, you have to choose suitably variable coefficients and sum about this derivative of f, derivative of g with proper order of derivative. Then one can show that this fg bracket n, this is for each n, we get a modular form weight k plus l plus 2n. And he said that if if n is bigger than or equal to 1, this is always a cost form with k plus 2 plus n. And there's a nice paper of Zagier in 1994 where he studied this Rankin-Cohen bracket, basically the algebraic structure of the space of modular form with respect to this bracket. And just one observe that if you take this zeroth bracket is nothing but the usual product, and this bracket, if you take these two variable things, then this is bilinear forms from mk cross ml to mk plus l plus 2n. All right. So now, in the case of the first theorem of Cohen, we are taking this n to be 0, and we are taking the product. Now we consider the general situations. So given a modular form with L, and consider this map TGN from the space of cos form with K to the space of cos form with K plus L plus 2n, defined by TGN of f equal to f comma gn. So for every g and n, we have this map from sk to sk plus 2l plus 1 defined by this bracket. And since we know that the bracket is a bilinear form, so we are fixing one variable, so this is going to be a linear map. And you see that t is 0, if n equal to 0 is the usual product. And generalizing theorem of Cohen, Herrero in 2014, he computed the adjoint of TGN for any n, which involve the special values of certain declared series. All right. So what are the modifications? Let's look this theorem of Herrero. So it takes k bigger than 6, L and R positive integers. So we are taking this for the convergence region. We take a modular form of 8 ml. It's not necessarily a cost form. So you take a modular form of 8L with coefficient Fourier coefficient Bm. And there are two cases. One is G is a cost forms, or if G is a non-cost form, so we have to assume these particular conditions that L less than K minus 3. Then image of any cost forms Fz of weight K plus L plus 2n with Fourier coefficient Am. So if you look this up to some gamma factor, you look this part, the summation, this is the m to the k minus 1, look the Fourier coefficient m to the k minus 1 from I to 0 to infinity, ai plus m, bi bar, and these particular numbers, these particular expressions that arise from the Rankin-Cohen bracket. And this is the special value at the point k plus l plus 2n minus 1. So basically, this is a cost form. So this is basically proving that this is going to be a modular form, or these are some modularity properties. So basically, this is the part using the Rankin-Cohen bracket, one generalized to using this differential operator Rankin-Cohen bracket. All right. So there are certain interesting application of this theorem. So basically, if you take special case of this f and g, so one can show this Rankin identity. Rankin proved in 1952. Basically, this tau m by m to the power 11 is nothing but minus 240 times this particular I plus m sigma 3i. This is the Rankin-Selvig type declared series for the Ramanujan tau functions and sigma 3. Here, the sigma 3 means sum over d cube, where d divisors of n. That the divisors functions. All right. So there are other kind of applications. These things I'm not going to that. So now we come back to Jacobi forms. So let's Jacobi forms is generalization of modular forms. So a Jacobi form with k and of index m. Sorry, there's something. Yeah. Okay, a Jacobi form with k and index m on SL2Z is a holomorphic function from H cross C to C, satisfy this transformation property. So there are two properties with respect to the group A, B, C in SL2Z, and other property with respect to the lattice. Yeah, so Z2. So we have this particular transformation property, phi of eta plus b by zeta plus d, comma z by zeta plus d is satisfied like some, this come from the modularity and this come from the particular lattice kind of thing. And we have the other property, phi of tau, comma z plus lambda tau plus mu, with this factor with phi tau z. So there are two properties here, one with respect to the group, or other with respect to the lattice. And this is a Fourier expansion of the form phi tau z is equal to summation C and R is coefficient depend on two parameter n comma r, q and zeta r, where q and zeta are the corresponding e 2 pi tau and 2 pi z. And here this r square minus 4nm, the condition come from similar condition we have in modular forms. All right. So in addition to that, we say phi the cos forms if C and R not equal to 0 implies r square strictly less than 4nm. All right, and the space of Jacobi form, so weight k, index n, we denote by jkm, and we have this cos form jkm cos, the space of all Jacobi cos form weight k and n. Also, we have this inner product, Peterson inner product for the Jacobi, the space of Jacobi forms. And with respect to this inner product, the space of Jacobi forms forms a Hilbert space. All right. So let me just tell this theorem of Chui, Kim, and Knopf. So they construct a Jacobi cos form using this following idea of Conen. So you take a Jacobi cos form of weight k plus L index m with this Fourier coefficient A and R, and you take a cos form, usual cos forms for the group SL2Z of weight L with this coefficient BL, with the coefficient Bn. Then if you fix this DG, if you take this Jacobi form, you take a Jacobi forms and multiply with G, you get another Jacobi forms, and that maybe is linear. And we are then basically they compute this TG star for that, and the TG star defined by this summation C and R Q and zeta R, where C and R is defined by up to some this is the kind of discriminant, and up to this gamma. This is the Rankin-Selbach type Dirichlet series related to a Jacobi forms and modular form that appear as Fourier coefficients with this special at the point k, the special value at the point k plus L minus 3 by 2. All right. So this is basically a generalization of the result of Conen. So you fix a Jacobi, you fix a modular forms, you take these Jacobi forms to Jacobi forms, just multiply with G, and try to find out the return wave with respect to the yield product. All right. So there is another generalization of this theorem to the case of Jacobi forms. So basically, you don't need to take a modular forms G, a modular form Z, but you can take that as a cos, that is Jacobi forms, and you can consider this wave from Jacobi forms to Jacobi forms and multiply with the fixed Jacobi cos forms. So here this, you take two cos forms, phi 1 and Jacobi cos form phi 1 and phi 2 with coefficient A and 1 R1, A and R, and the coefficient this phi 2 has B and R. Then we have this particular the forms defined by this particular arrangement C and R, Q and zeta, where C and R is, forget about this part, you look the second line. So A n comma n plus n1 r comma r1, that is shift in n1 n and r. For C and R is the shift in n part, also in the r part, and B n2 r2 is the same way we define. And this is the particular special value of k1 plus at the point k1 plus k2 minus 3 by 2. So this is basically is the special value of coming from the Jacobi forms play into this picture, and one can get a Jacobi forms within these spatial values. So basically, actually, this context of in the case of Jacobi forms, generalizing the theorem of Conen. All right. So now we have this Rankin-Cohen bracket for Jacobi forms. So we define this heat operator Lm phi. So this is a 2 pi Im del by del tau. There are two phi tau z. So Jacobi forms on H cross C. So there is tau variable, upper half plane variable, and there is complex variable. So we define this operator. And there is a theorem of Choye. So you take a Jacobi forms of weight K1 index M1. You take a Jacobi forms of weight K2 index M2. Then we define the similar kind of bracket for every n. We have a functions. So this is basically the similar way, choosing proper binomial coefficients. And we have this LM1 R times, LM2 n minus R times apply on the phi2. So these particular combinations, we are applying this LM. LM is the operator that play into picture in this case of Jacobi forms. Then we saw that then the theorem Choye say that this phi1 comma phi2 and bracket, this is a Jacobi form of weight K1 plus K2 plus 2n and the index M1 plus M2. And if n bigger than equal to 1, then this Röntgen bracket gives you a Jacobi cos forms. And similarly, we have this bilinear mapping from JK1 comma M1 to JK1 M1 cross JK2 M2 to JK1 plus K2 plus 2n M1 M2. All right, this is exactly generalization of the usual Röntgen bracket to the Jacobi form setup. Okay, so we note that here the same case you can consider about the adjoint map of adjoint of linear maps. So if you take n equals 0, you get the product of Jacobi forms, and you take this fixed Jacobi cos forms psi, and you take an integer nu, then you can define this pi psi nu from JK1 M1 cos 2 JK1 plus K2 plus T nu M1 M2 cos defined by this particular bracket. So as earlier, this is going to a linear maps. So you can talk about the adjoint of this map with respect to Peterson inner product on Jacobi forms. So basically, we have this, we're talking about this particular inner product, and we're trying to find what is this map T star psi nu. All right. And with Avas, we prove the following theorem. We take these integers K1 bigger than 4, K2 bigger than 3, M1 and 2 are natural number. We take these Jacobi cos forms with coefficients A and R, and you take any cos forms of phi with the Fourier coefficients B and R. Then we can compute this adjoint map, and the adjoint map gives you this C nu and R with Fourier coefficients, and C nu and R defined by this. So forget about the first two part, depend on the A, M, and R part, and the coefficient coming from here. And this is basically this the Röntgen-Selbach type declared series for Jacobi forms coming to the picture, and we have this special value K1 plus K2 2 nu minus 3 by 2 that's coming to the picture here, and this particular coefficient is just come from the Röntgen bracket of modular form, Jacobi forms. Okay. So this is basically the generalization of theorem of Herrero to the case of Jacobi forms using Röntgen bracket. So one can get some interesting application of this kind of the similar kind of theorem Herrero gives this for these Ramanujan tau functions using the structure theorem of Jacobi forms. One can get some arithmetical application of this theorem, similar theorem. I'm not mentioning here. All right. So just I would like to some further generalization to this. So what we construct for the Jacobi forms, the Röntgen bracket given by Choye is a very special case of some more general bilinear differential holomorphic operator on the Jacobi forms. And Bokor proved in 1999 that the space of holomorphic differential operator raising the weight nu of each of dimension 1 plus nu by 2. So basically, there are many differential operator one can consider. So then Choye and Nyholzer, they computed this differential operator explicitly, and one can, with Avas also, we generalize the work of Herrero to all the linear maps constructed with this differential operator, which appear in this proceeding of automorphic forms, US automorphic form, building bridge. So then there are also generalization to the Ziegler modular form for genus 2 with Abbas, and there are these Abbas and Arvind, they work out for habitable modular forms, and they give some nice applications of those theorems. And the generation of Hilbert modular forms with Moni Kumari, she did in her thesis, generalizing this Hero's theorem to the case of Hilbert modular forms. All right. So let us, recently we talk about this Jacobi forms of higher degree or several variable, basically Jacobi forms of H cross CG of this, they are now Jacobi forms of matrix index. Let me just give a brief report on that. So here the Jacobi group is gamma 1 similar to this ZG cross ZJ. I'm writing as a column vector, so I have a G cross 1 I'm writing here. And this act on this group H cross CG, H on the space H cross CG, defined like this. So this basically we are generalizing the action of Jacobi group to the bigger Jacobi group is the same way. I think just extending this many component in the lattice part, and we define this the Jacobi forms for H cross CG. So let K be a integer, M be a positive definite symmetric half-integral matrix G cross Z matrix. So for any gamma, A, B, C, D, and lambda mu in this Jacobi group, and for a complex valued function H cross CG, we define this stroke operator. This is basically generalizing the Jacobi forms, the usual part. So theta plus d2 by minus k. This is the E2 pi. This means E exponential A means EA means E exponential 2 pi IA, and this is basically this minus C by theta plus D, and this symbol here M another this M matrix is another matrix, and A square bracket B means B transpose AB, where B is the transpose of B. All right. So this is the these two combine the action of the Jacobi forms part here. All right, and this is the action of gamma on tau z, and gamma is element of this type, and tau z element of this type. All right. So after defining the stroke operator, so let's define this JKM for this integer m and integer k and this matrix M. The space of all Jacobi forms weight k index m on this Jacobi group, then the space of all homomorphic functions from H cross CG1 to CG, CG cross C, satisfying this automorphic factor, automorphic properties, and we have this Fourier expansion of this type C phi n r e n tau rz, where the restriction is 4n minus n inverse r tau. This define exactly the one B transpose AB, the last slide. Okay, and we say this is a cost forms if and only if C phi n r equal to 0 whenever 4n equal to m inverse this square bracket at the transpose of R. And we denote the space of Jacobi forms by JKM cos. And this also there is inner product on the space on JKM. So So with respect to this inner product, this JKM cos is a finite dimensional Hilbert space. So there are point carry series, and there are eigenstring series. One can get example of this in a similar way. And we have this theorem, we work it out with Ramke in 2010. These Fourier coefficients of this kind of Jacobi forms grow like this. So D is basically the discriminant of D is defined by this M tilde r tau minus 4n. This is the determinant of M, and this is the way these functions grow, and this Fourier coefficient grow. And we have this heat operator in this case. So for every positive definite symmetric half-integral G cross Z matrix M, we define this heat operator Lm is exactly this heat operator apply in the case of visual Jacobi forms. We are in this generalization to the matrix index here. This is basically the determinant M, and this is the Mij, is the ith cofactor of matrix M. All right, and for G equal to 1, we have seen this is equal to the usual heat operators L small m, which is studied in the Achilles-Jaeger book in theory of Jacobi forms. And here we see that the LM act on this element E and tau R Z. Basically, the discriminant goes out for n mod m in the m tilde r tau and E and tau, where this m tilde is the matrix of cofactor. So using this LM, one can define this Rankin-Cohen bracket in a similar way that's defined in the usual case. Basically using this LM, the heat operator. Yeah, so we proved with Ramke in 2010 that this particular expression, generalizing this theorem of Choye, one can produce Jacobi forms out of using this heat operator and choosing this particular choice of these binomial coefficients. Sorry. All right. So now come back to this adjoint of the linear maps. So we have a Jacobi cos forms psi with pick the Jacobi cos form and integer nu and t psi nu. Define this map from jk1 m1 cos to jk1 k2 nu plus m1 plus m2 cos. In the same way, we consider these linear maps. And this we can talk about the adjoint from the space here to here. All right, defined by this particular inner product. All right. So we can talk about this Fourier coefficient of this, or what kind of Fourier coefficients appear in the construction of cos forms. All right. So this result appeared last year with IGNT. So with Avas, we proved that basically if you take a cos forms of weight K2 M2 with the coefficient C phi N1 R1, then we take a another cos forms. You can consider this map T psi nu star from JK cos to K1 K2 to nu to M1 M2, and basically what we proved that this the Fourier coefficient C and R that appears as coefficient of this adjoint map is basically forget about this part again. This is exactly the same way it is written. It comes very naturally like the modular form case or Jacobi form case. And this is basically the last part. The Rankin-Selberg type declared series for Jacobi forms of higher degree appears here, and we get the same kind of exactly expressions with these spatial values at the point k minus g minus 2 minus 1, and one can as in arithmetical applications we remark that this we can find this the applications of f comma g. You take a modular form Jacobi forms with of suitable weight f, and you take g, you take the Eisenstein series g, and then you take the inner product. So one can find explicitly using this kind of idea also. All right. So that's all I'd like to tell. Okay. Thank you very much.
So,
yeah.
Thank you, sir, for the nice talk. So, are there any questions?
Yes, I have a few.
Yeah, all right. I'm just switching on my video. Just a minute. Yeah. Okay, go ahead. Yeah.
Yeah. So here in the second slide,
second slide.
Yeah.
All right, go to the second slide.
Where you showed first time this shifted Rankin-Selberg series.
Yeah.
Farkas form.
Yeah, second slide.
I think so, if I remember correctly. I don't know.
Okay,
Yeah, exactly. This one. Yeah. So this series, you said meromorphic continuation has been studied by someone. Yeah, good.
Yeah, good. Yeah.
Yeah. So in what context he studied? Like this is appearing in your adjoint map, but in what context he studied this series?
Oh, this is nothing to do with what Anton Good studied. Basically, he studied this meromorphic continuation of this particular. Nothing to do with adjoint maps. Yes.
He
I think he was studying some average of Fourier coefficients
Yeah.
related to. Okay, so you can have this average of Fourier coefficient associated to Ramanujan tau function.
okay.
So Anton Wood, he is using this Dirichlet meromorphic continuation of this Dirichlet series to study the average of Fourier coefficient related to any custom.
Okay. Okay.
Yeah,
So this is nothing to do with adjoint maps. Yes.
Yeah. Okay. And the Dirichlet series, which is coming in further context like Jacobi, Farm, Giegel, etc. So
Yeah.
for them also meromorphic continuation is known, or it is just a Dirichlet series?
I don't think so. Is known.
No, it is not known. It is not known. But something is there for like twisted thing is there for Martin newspaper. There is some Rankin Selber Dirichlet series associated to Sigal custom by Hughes Martin and Imamoglu. There is some paper, but not exactly this series.
But I don't think they take a shifted one.
No,
They
no,
take
it's
No,
not the
it is
one.
not.
It's not the one.
For shifted, it is not there.
Yeah.
For shifted, meromorphic continuation is not there. So yeah.
okay. And just another question that like Jacobi forms, they appear as Fourier Jacobi coefficient as local information they give. So can we go from one to other like Jacobi forms result to Giegel form in place of going to Giegel form and working explicitly there?
What is say? Which context you are doing? Come the repeat the question.
So the in the context of adjoint map itself,
Yeah.
so we have this adjoint map evaluation in each context like Jacobi form, Giegel, especially Jacobi Giegel, and
Yeah.
Jacobi forms are just local information for Giegel modular form, like they are Fourier Jacobi coefficients.
Yeah. Yeah.
So by any chance,
Yeah.
having result for Jacobi forms, we
Yeah.
can
Yeah.
deduce result for Giegel modular forms.
Yeah. From Jacobi to Ziegel, this Fourier Jacobi, there are the adjoint maps are there.
No,
Mm-hmm.
no, sorry. I think he's asking about suppose you have result for Siegel, how to
Yeah.
come
Oh, okay.
for your Jacobi coefficient. So how
Yeah.
to come to so yeah.
No, no, those kind of results.
In principle, it should be done if you
Yeah.
consider this Fourier Jacobi extension. So you have Jacobi form. Now you have to take theta decomposition. So there is a relation between Daikin-Cohen bracket of theta decomposition with Jacobi forms. So
Okay.
then it can be done, but I means calculation will be actually obviously it will be
Okay. And just last question, I was wondering, what is the situation in label if I start taking label higher label modular forms?
For level, I don't think it will play any role. I think one can generalize to level also, I guess.
Okay. Okay. No difficulty
Yeah.
seems
So
right.
for the easier case of modular forms, one can take general level. So,
Okay.
but they not one can write it down. Yes.
Okay. Okay. Thanks, Sam.
So one more comment, maybe recently Sujit and his collaborator, they have done for this Hermitian model,
Yes.
Jacobi form model.
Yeah. For Hermitian modular forms.
Hermitian Jacobi form, not model. I don't know modular form, but Hermitian Jacobi form it is done.
Yeah.
So, are there any more questions? So, if not, then let us thank the speaker again. And,
Thank you. Yeah.
and I think we have 5 minutes. So after 5 minutes, we'll start the next talk.
Yeah.
Yes.
Abhas, be here. I will set up my slide and
Yes. I'm here. You can
So I
share.
will
You
stop
can
sharing. Yes.
yes, you can stop sharing now.
Yeah. Stop presenting. Yes. Now fine, I guess.
Now you.
yeah, I am going to share Abhas.
Yes.
Let me.
Yes. So now please go to this full screen.
Yeah, let me go to the full screen mode.
Yes. Yes. Fine.
What about now?
Yes. Now it is good. It is good.
It is good.
Yes.
And just tell me if it is moving.
Yes. Yes. Yes.
So right now I am on the page of starting. Yes, Ramanujan,
Yes.
uncertain.
Yes.
Now.
Yes. Yes. Yes.
Okay.
Yes.
Thanks. So Abhas, maybe I will keep switch off my I will keep video switch off so that connection remains okay. I think.
Okay.
Other
No problem. No problem. If you are comfortable with that, that's okay.
yeah, and once talk is over, then I will switch on the video and
Yes.
everything. Okay.
Sure. Sure. Sure.
So let me know when I suppose to start. Then I will put it in full screen mode.
Okay. Okay.
Okay.
Maybe we can start now. So the next speaker is Professor Karamdev Sankdar from ISER Bhopal. So he did his PhD from HRI Allahabad under the supervision of Professor B Ramakrishnan. Then he was in IMSC for postdoc. Then he moved to University of Chile for postdoc. And after coming back to India, he joined ISER Bhopal as a faculty member. He works in Jacobi forms, modular forms of half integral weight, and L function associated to modular forms and several automorphic forms. So now today he is going to talk about quasi-modular forms and Dirichlet series. So I request Professor Karamdev Sangdar to deliver his talk.
Thanks, Abhas. Kind introduction. What is happening? Am I audible? Abhas?
Yes, you are audible.
Sound is clear?
Yes, very clear, very clear. Please
Okay,
go ahead.
okay, thanks. In between, if there is any problem, then let me stop me and let me know.
Okay, sure.
Yeah. So thanks, Abhas, for giving me opportunity to speak here and to listen such a nice talks. Today I will speak on quasi-modular farms and Dirichlet series. So basically, quasi-modular farms are generalization of modular farms in some sense, and they rise very naturally. If you take modular farms and take derivative of modular farm, what transformation property they satisfy? They satisfy they satisfy some transformation property which is not as nice as modular farms, but that's why they come in the category of quasi-modular farms. Everything I will define very clearly in a moment. This is based on a joint work with my colleague here, Ajit Pan. So let me set up the notations and define quasi-modular farms. Good. Before me, Professor Sahu was talking, and already he had defined modular farms, etc. Modular farm, we know what is that. They have modular farms are certain holomorphic functions on the upper half plane, which have nice transformation property with respect to the bilinear transformation if we apply SL2G action on the upper half plane. So let me go quickly one by one. So H is Z belongs to here. H will always denote the complex upper half plane. SL2G 2 cross 2 integer matrices with determinant 1. SL2G acts on H. ABCD will take Z to AZ plus B by CZ plus D. Throughout the talk, we fix our positive even integer K, which will stand for base, and P non-negative integer, another parameter here, which will stand for the depth of the quasi-modular form. With quasi-modular form, two parameters will be associated. One is weight, other is depth. And I am taking P non-negative. So whenever you will put P is equal to 0, everything will reduce to the theory of modular forms. So at any point, if you want to see whether it is getting compatible with the theory of modular forms, whatever has been happened there, put P is equal to 0 in the theorem. So let me define quasi-modular form formally. So quasi-modular forms are weight K and depth P, another parameter depth in compared to modular form. This is again a holomorphic function F from H to C, which has some little twisted transformation property. So in the modular form, we saw that F slash K gamma Z, that is F of AZ plus B by CZ plus D, is equal to CZ plus D power K F of Z. But in quasi-modular form, this may not be true, that F goes to F itself. But what we are demanding here, there exists holomorphic functions F0, F1, F2, Fp, P plus 1 many, such that Cz plus D power minus K F of AZ plus B by Cz plus D can be written as combination of those holomorphic functions Fj, Z with the factor C by Cz plus D power J. So not that bad. We are deviating little bit, but not that bad. And in this transformation property, if you take gamma is equal to identity, you can immediately see that the left hand side will be F of Z, right hand side in identity, the C entry of the matrix will be 0, so it will be just F0Z. So in fact, in the component function, the zeroth components corresponding to any quasi-modular form, it will be itself. And one can show that the last component Fp, it will be actually a modular form for SL2G. So these two informations you can have in your mind. And the other condition is similar to modular form, which we will demand for each Fj, that Fj has a Fourier series expansion of this form, Ajn q power n, to make sure the holomorphicity at the cusp I infinity for each component. What are the examples of quasi-modular form? The best example, the first and obvious examples are modular forms. Any modular form, they are quasi-modular form of weight K and depth P. Especially Eisenstein series, which is very familiar to us. Eisenstein series is defined in many forms by using the cosets and double sum, but here I am writing the Fourier series expansion of the Eisenstein series, which I will be using here and there again in the talk. So this is 1 minus 2k by bk summation n greater than or equal to 1 sigma k minus 1 of n q power n. These are the Eisenstein series. They are called Bate K Eisenstein series. And what interesting happens that due to absolute convergence of not this series, I am not talking about absolute convergence of this series, but if you start with the double series representation of EKZ, due to the absolute convergence of that series, EKZ, it is a modular form of Bate K if K is greater than or equal to 4. Note that I am taking K always even positive integer. But E2 doesn't satisfy the modular property. It deviates from the modular property and it satisfies a little modified transformation property like this. Cz plus d power minus 2 E2 of Az plus b by Cz plus d is the first one is E2z and the second one C by Cz plus d times I pi. Now you can see that E2z is a quasi-modular form of Bate 2 depth 1. And what are the two components associated to the quasi-modular E2? That is, the first one is F0 is E2z itself. The second one, F1 component, is I pi, which is Bate 0 modular form. So this E2 is Bate 2 depth 1 modular form. Quasi-modular form. And you take any modular form, as I said in very beginning, that take any modular form and take derivative of this, take double derivative of this, triple derivative of this, they all will be quasi-modular form. So that's why if you allow forms to be quasi-modular, then they will be closed under the differentiation operator. Differentiation of quasi-modular will be quasi-modular, which is not true for modular forms. So we have ample number of examples for quasi-modular forms. And another fact I want to tell about quasi-modular form, as in the case of SL2G modular form is a polynomial in E4, E6, and in a quasi-modular form is a polynomial in E2, E4, E6. Note that I am talking for SL2G. Let me come to an interesting example. So the famous paper of S. Ramanujan, Srinivas Ramanujan, in that paper at one place he considered this double series for any two positive integers L1 and L2, phi L1 L2 of Z, this double series n power L1, m power L2, q power mn. And if you take mn is equal to some a and rearrange this double series, you will get this series summation a is equal to 1 to infinity a power L1 q power a, and the coefficients will be sigma L2 minus L1 of a. Now the point is, we start with this double series and ask the question, what about transformation property of this series, whether this series represent any nice structure on this, whether it is modular, quasi-modular, anything. And in that paper, at least Ramanujan gives many examples by taking the particular values of L1 and L2, and ultimately he deduced that for if you start with okay, I will come to the conclusion in the last bullet point. Let me just go one by one. So you observe this, if you take L1 is 0 and L2 is equal to L, it will be just L1 will, this means a power L1 will go away and it will be sigma L2 of a. And if you remember, sigma L2 of a, exactly sigma k minus 1 of a was appearing in the Fourier series expansion of Eisenstein series. Therefore, I can write it sigma L2 plus 1 minus 1 of a q power a, and the first term I can add in this, that was the constant term. Then what will happen, this if I modify, if I just add this term extra, then the new series will be just constant multiple of the Eisenstein series EL plus 1. Please note that L is odd, therefore L plus 1 is even, and our job is settled. At least L1 is 0, L2 is L. Then this is nothing but constant multiple of Eisenstein series. Once phi tilde 0 L is constant multiple of Eisenstein series, And if you just look at carefully on this expression, we will get that phi L1 L2 is nothing but L1 derivative of phi tilde 0 L2 minus L1. And already I know that phi tilde 0 L2 minus L1, this is a modular form, constant multiple of Eisenstein series. If L2 minus L1 is odd, therefore this whole thing will be quasi-modular form. Therefore, phi L1 L2, whenever L2 minus L1 is odd, for better rhyming, if you say L1 plus L2 is odd, then it is a quasi-modular form of bit L1 plus L2 plus 1 and depth L1 plus 1. I think it is, yeah. So that is there. Since after derivating one time, weight get increased by 2 and depth get increased by 1, that's how you get weight and depth here. But what remaining is, what about if I take L1 plus L2 even? So the question is, what about if I take L1 plus L2 even? In particular, you take L1 is 0 and L2 is L, then what about this series, summation n greater than or equal to 1 sigma L of n q power n, but now L is even. In Eisenstein series, this k minus 1 is always odd. What about this series? Whether it has some nice structure. I will come back to this question to answer this, but before that, I will introduce Dirichlet series. Using that Dirichlet series, I will answer this question. So, let me attach Dirichlet series to quasi-modular form. So, F is a quasi-modular form of weight K and depth P. And just by using structure of the quasi-modular form, one can immediately get that the coefficients A, J, N. Please note that if some quasi-modular form is there, it comes with components F1, F0, F1, F2, Fp from the transformation property. A, J, N can be is nothing but big O of n power k minus 2j minus 1 plus epsilon. So the coefficients has bound. This means I can start with Dirichlet series. At least it will converge in some half plane. So I will attach the general simple Dirichlet series exactly in the way it is done for modular forms. Take the coefficients. So to any component function fj, I will attach Dirichlet series. So to a given quasi-modular form F, there will be P plus 1 attached Dirichlet series for j is equal to 0, 1, 2, P. And since here I am taking j can be anything 0 to P, for safe side I am taking real S greater than P. In that, at least all P plus 1 Dirichlet series will converge. So given any quasi-modular form, I have attached P plus 1 Dirichlet series to that by using the component function. Now completed Dirichlet series will be just in the same way as it is for modular form. We will add gamma factors and 2 pi power minus s. What happens? What are the analytic properties for this Dirichlet series? That will come to the next. So analytic properties of Dirichlet series, first thing is that analytic continuation. So if you take any lambda fjs P plus 1 Dirichlet series for the quasi-modular form, then it admits a meromorphic continuation to the whole complex plane and satisfies this functional equation that is proved in our joint work with Ajit Bhan. And it has, moreover, its poles are fixed exactly in the same manner as it is for modular forms. Please note that we will have more poles, and this is due to since transformation property is not so nice as for modular forms. And functional equation also will involve many components in the right hand side, whatever component appear in the transformation property. So
hello,
yeah.
Can you repeat the last line? Your voice was breaking. Can you repeat the last line?
Yeah, last line was that we get meromorphic continuation in the whole complex plane and satisfy the functional equation, and it will have more poles in compared to modular since it has many components in the transformation property. Abhas?
Yes, fine.
Fine?
Yes, okay, go ahead.
Am I audible?
Yes, now you're audible.
Okay. So And as I said, at any point you can put j is equal to 0, and you will see that this functional equation, this every analytic property will, no, sorry, j is equal to p. If you want to test with modular form, if you put j is equal to p, everything will reduce to the modular form Dirichlet series, since fp is modular form in those components, p plus 1 many. In particular, since f0 is equal to f, lambda fs will have analytic continuation in S plane with the poles from 0 to k minus p. So pole this we will have p plus 1 poles for quasi-modular form F, and it will be holomorphic as usual if the zeroth coefficient are 0 in all the components. Now, I will not use Euler product property at all throughout the talk, but just for completion, I want to just point out here that if you take any quasi-modular form and define an Hecke operator exactly in the same way in modular forms, one can talk about quasi-modular eigenforms, etc. And there are it has been tagged at several places. And once it is quasi-modular eigenform, one can have the multiplicativity of the coefficients, and then one can expect in that case LFS will admit Euler product as well. Now let me come, after attaching the Dirichlet series to quasi-modular and studying in analytic properties, let me come back to the Ramanujan's phi function. And in that case, let's recall phi L1 L2 Z was summation n greater than or equal to 1, and this was the coefficients d power L2 n by d power L2 minus L1. In that way I can write. Now just look at phi L1 L2 and take the coefficients and form the Dirichlet series without bothering what structure this form has, and it will be just, this is divisor function, so it will give us lambda phi L1 L2 s, it will be 2 pi power minus s gamma s, this be attached for completion, zeta s minus L1, zeta s minus L2. And the point is that zeta s minus L1, zeta s minus L2 and gamma s, this whole completed Dirichlet series will have poles at negative integers minus m, such that minus m minus L1 minus m minus L2 both are odd, so that they don't cancel the pole of the gamma at negative integers. And this can be chosen such, m can be chosen such that minus m minus L1 minus m minus L2 will be both odd, since L1 plus L2 is even in our case. So this means that lambda phi L1 L2 yes, the attached completed Dirichlet series to this form. If L1 plus L2 is even, it has pole at negative integers. On the other hand, we saw when we attach Dirichlet series to quasi-modular form that the function, the attached Dirichlet series should not have any pole in the, it has analytic continuation and all poles are only 0 to p in the positive side. So that's why we get contradiction, and therefore this function c phi L1 L2 Z, this cannot be at least quasi-modular form for any constant c in C if L1 plus L2 is given. And for completion, just I want to put this question in front of you. Certainly it would have been interesting if I would have said that what transformation property or some nice property it has, the L1 plus L2 even case, but we don't have anything. We had just that result that it is not a quasi-modular form. What happens if I take for L even and just put L1 0 and L2 L, this lambda phi 0 L s forms phi L1 L2. Now another application we will get that signs of the Fourier coefficient. As we know, the moment we study Dirichlet series attached to any automorphic form, the point is that we can expect for result for the signs of the Fourier coefficient, and same thing will happen here. If f is a quasi-modular form, only thing is that poles I want to kill. So to kill those poles in the analytic properties, I have to take component function such that I have to put the condition that constant term of the component function should be 0. Then this sequence an, which are the coefficients of f, they will be oscillatory, and where it can be used, certainly if you take a modular form and take the derivative, obviously sign change will come from the modular form, since after taking derivative it just add in the coefficient, it just get multiplied by n, which doesn't change sign. But the point is that if I take a cos form f1 and a cos form f2 and take suitable derivative of them, so that weight remains same. Suppose f1 has k1 weight, f2 has k2 weight, such that k1 plus 2 L1 is equal to k2 plus 2 L2, so that it is k1 plus 2 L1 weight quasi-modular form. Then it is linear combination of coefficients of derivatives of modular forms, not modular form, cos forms, and but we will have sign change result for these forms as well. So there this criteria can be useful. Next, I want to give another application that after studying Dirichlet series, we thought why not to get result on the lines of Hecke, as Hecke has converse theorem for modular forms, that a modular form, if and some given formal power series, summation a and q power n, such that an has nice bound, if and only if this has modular form structure, if and only if the attached Dirichlet series has a nice analytic property, that it is entire bounded in every vertical strip and it has nice functional equation, lambda fs is equal to this. So this was the result of Hecke, and it is very relevant in our context, since what we are going to do, we are going to get result analogous to Hecke's converse theorem for quasi-modular form. But those are due to many components, those are lengthy calculations, so I am not going to get into in very detailed calculation. What I will do, I will take Hecke's proof and go line by line Hecke proof, but I will just indicate where we have to change due to quasi-modular form. So let's start 1 implies 2. Let's assume, so here first assume that suppose I am starting with the f a modular form, I want to get analytic properties of the completed Dirichlet series lambda fs. What we do, it is a standard technique that be lambda fs be write as Milling transform of the function f on the imaginary axis by removing the constant term, so that it has exponential decay, and later it turn out to we can have integral which is entire. So, and then break this integral 0 to infinity into two parts, 0 to 1 and 1 to infinity. And for the part 0 to 1, we use the modular property of f, modular transformation property. And if we use modular transformation property, then I can change 0 to 1 integral as well, 1 to infinity, and we will get 2 1 to infinity integral. And here we can see the symmetry, and that's how we get Dirichlet series attached to modular form functional equation. Here what will happen when we will do 0 to 1 to 1 to infinity, when I will change iy to minus 1 by iy, due to quasi-modular transformation property, it will contain many combinations here. And if we can manage that well, then we will get functional equation for the Dirichlet series attached to quasi-modular form. And exactly that's what we do. In modular form, we immediately get lambda fk minus s is I power k lambda fs, but here we will get certain combinations, and we have to certain combination of integrals, and we have to just adjust that to get Dirichlet series attached to the component functions. And that's what we do with these integrals. And in that way, we prove the direct part. What about converse part? If you recall the Hecke converse theorem proof for converse part, it is just inverse Milling transform of the given completed Dirichlet series. First, f of it, which is summation a fn e power minus 2 pi n y. By using inverse Milling transform, that can be represented in terms of the integral of the completed Dirichlet series. And then we use standard Stirling's estimate, Riemann-Lindloh principle, and functional equation of lambda fs to get the functional equation of f of the modular form f on the imaginary axis. And since f is holomorphic due to the bound on the coefficients, we get that this will hold on the whole complex plane. And the point is that SL2G is generated by two generators, S and T, and that will establish the modularity condition for f. Since f was given by Q series, therefore
with respect to the translation matrix, transformation property is immediate. Only we had to get with respect to yes, that we have got. In quasi-modular form, exactly we start with the with this inverse Millen transform. But the point is that for quasi-modularity, we don't know if we just whether we go and directly establish the quasi-modularity of F with respect to the inversion matrix. Yes, in that case, what happens with if we can prove a simple lemma which will say that it will be sufficient to establish quasi-modularity for F if we establish certain transformation property for each component. And that was natural, since for each component we had functional equation, so somehow we had to use that. So we use for each component's functional equation and managed to get quasi-modular property of the F. So that was the converse part for that. And I think I have 4 minutes left. So what about this after this converse theorem? So yeah, so let me just state in one slide what is the converse part. So the direct part was stated when I wanted to use it for the phi L1 L2, but converse theorem will look like this. We have to start with p plus 1 sequences AJN, any sequence of complex numbers. Only thing is that it should have appropriate bound, and then we consider this formal power series which will define holomorphic function. If each lambda fjs has exactly those analytic properties which we showed in the direct part while using it for the phi L1 L2, then F naught, that is F naught will be a quasi-modular form of bit A and Fp with component functions F0, Fp. And for p is equal to 0, it is AK converse theorem. For p is equal to 1, it is IMS thesis under Professor Yves Martin. This is for general p, but for SL2G. Just let me comment in last one moment what will happen if I take label quasi-modular forms. What kind of Dirichlet series and what kind of converse theorem we can expect. In that case, this is something which is going on with the other collaborators. So we are just in this one we are trying to get converse theorem for gamma 0 n quasi-modular forms like analog of Bell's converse theorem. But in that one, I want to just emphasize on one difficulty. The first difficulty which we faced, if I take F is a quasi-modular form, then the point is that the Fricke involution plays a crucial role in the Bell's converse theorem, since Dirichlet series, the functional equation, they get associated from one side to other by F to F slash Wn. But the point is that if I take quasi-modular form, then I apply the Wn operator in the usual sense, it need not be quasi-modular. So what to do in that case? What happens? If we take F a quasi-modular form with component functions Fj and collect them in this way, then they will turn out to be satisfying one nice transformation property, and this new function will be if I apply Wn on this new function F, capital F, that will be again this kind of function. And if you remember to this terminology, these kind of functions are called nearly holomorphic. So by going to nearly holomorphic, certainly we can resolve this first difficulty, that under Fricke involution quasi-modular doesn't go to quasi-modular, and few more difficulty will arise, since we know that in Bell's converse theorem the main difficulty was the gamma 0 n is not generated by just two matrices, so one had to take corrector twist Dirichlet series, which we can manage. So ultimately what will happen if I start with p plus 1 component Fj, I twist it by some primitive Dirichlet corrector psi with conductor m psi, and then capital F psi, and apply to Wn, it will be behaved under Wn, and that's how we could do that. And outcome will be hopefully an analog of Bell's converse theorem for quasi-nearly holomorphic modular forms. And immediate consequences will be whatever phi L1, L2, etc. I told, they will, and using Dirichlet series, we can say that they cannot be quasi-modular for label as well, sign change it, etc. But we are looking for some more applications by using Bell's-Converse theorem. Okay, thank you very much. I stop my talks here.
Okay, thank you for nice talk. So, are there any questions? Yes, Manish.
Yeah, can you go to that functional equation which you wrote about that tan one? Actually, I'm little bit confused.
This one, Manish?
Yeah, exactly this one.
Yeah,
So here L is even.
yeah.
Yeah. So L is even. Now what I am saying that what is the difficulty? Like I am just simply writing tan and then taking sine and cos to the other side, and this seems like going S goes to L plus 1 minus S, and it satisfies. So like what?
No, sine and cos, if you write tan as sine pi s by 2 by cos pi s
Yeah, but I'm saying that the completed Dirichlet series is not this one, lambda phi 0 ls, but with the factor of cos, basically. That would be like the completed one for
But
me.
the point is that aim is to take this functional equation and invert it to get some
Yeah,
transformation property for phi 0 L.
yeah. So then I have to
And
look.
there, if you remember, then we just we change the first we change the line of integration from one side to other side and make sure that things work. Horizontal line integrality, etc. They go to 0. The point is that there you have to use functional equation. So things are not that easy. I am not even I tried that, but I couldn't get. I did not.
Yeah, because
I
no,
couldn't get it.
no. Why I am saying so? Because as of I know that
Uh,
Mellin transformer sine and cos are related with each other. So uh, like I think only thing is that to take the Mellin transform of this completed one. So if I just take with the cos and then take the Mellin transform, possibly I will get exactly what is on the right side. So it would be related. Yeah, maybe.
the point is that if you can get a transformation property uh, in the similar way, ultimately it will turn out to be having some nice transformation property, which may lead to quasi-modularity. But it is not quasi-modular and modular. So the point is that once you apply inverse Mellin, there will be subtle points.
Okay, maybe I'm missing. Yeah. Okay.
Okay, so Arvind, do you have any questions?
Yeah. So can you please go to slide number 18?
Yeah.
No, I'm sorry, slide number 17, just before that.
Okay.
So here you are saying that this free K involution operator preserve the space of nearly holomorphic modular form, right?
Yes.
So what is the corresponding action on the space of quasi-modular form you got?
Correct. Good question. So let me just say this. I wanted to emphasize, in fact, but so the point is that now we will not define f slash kwn in natural way. What we will do, this fz is nearly holomorphic, and f slash kwn, whatever component. So f slash kwn is again nearly holomorphic. So I can write in terms of the components. So I will, so Dirichlet series of F, the components of F will get related to the Dirichlet series of Fj tilde. In that sense, not in F slash Wn in that sense. And
so
I will define this Fj tilde as the modified image under Wn.
So what I understood is this thing that you have a quasi-modular form, small f, you got the capital F corresponding nearly holomorphic modular
Yes.
form.
Yes.
Then you got F0 tilde, right?
Yeah.
F0 tilde. that is the corresponding quasi-modular form for the F/KWN.
Yes.
So I'm asking, what are the properties of F0 tilde? Like, what are the labels? What is the label of that F0 tilde, and how it is connected with the small f?
Okay. So F. See, the point is that F0 tilde is again a quasi-modular form
Yes.
of the same weight and depth as F0 in F. Only thing is that this F0 tilde is not just F0 tilde is not F0/KWN. This F0 tilde is coming from the after applying WN to the nearly holomorphic modular form.
Okay.
But these F0 tilde, F1 tilde, F2 tilde, etc. will remain quasi-modular form as they are components of nearly holomorphic.
Okay. Thanks.
Of same weight and depth. Yeah.
Okay, so I have one question. So in the last slide, you are writing this possible outcome. So do you already have the converse theorem for nearly holomorphic, or you are expecting this?
Yeah, almost we have to see very carefully each step is correct, but roughly it has been written down.
And can you say something about weakly holomorphic modular forms?
No, weakly holomorphic in what sense?
No, like nearly holomorphic and weakly holomorphic, there is a correspondence between these two, right?
Nearly holomorphic and weakly holomorphic.
No,
I don't know what
no.
is
There is no such connection. So weakly holomorphic, actually, you are allowing just the poles for a modular form, right?
Yeah, but the point is the moment you allow poles at cusp, those Fourier coefficients will not have polynomial bounds. So we cannot start considering Dirichlet series in this sense. Yeah.
And just a remark that probably weakly holomorphic modular form has infinite dimensional space, right? I mean, the space is infinite dimensional. While nearly holomorphic modular form, you know that all the nearly holomorphic modular forms comes from the space of modular forms. In many ways, they are not new, but weakly holomorphic modular forms are quite mysterious in many ways.
Yeah, so in this simple sense, I don't see how we attach Dirichlet series even to weakly holomorphic modular form.
Okay, thank you. So, okay, so I think if there are no questions, let us thank the speaker again. We have now we have wait for maybe 7 minutes, and then we shall resume at 4 for the next session.
Abash.
Yes, sir.
Yeah, in HRI, in functional analysis, who is there? Do you know, Professor?
Yes, not functional analysis, I think harmonic analysis, Professor Ratna Kumar is there.
Mm-hmm. But particularly in function analysis, nobody.
Not in functional analysis.
Okay.
Harmonic analysis.
Harmonic analysis.
Yes.
Name you told, or what is the name?
Professor P. Ratna Kumar.
Acha, P. Ratna Kumar. Hello.
Karamdevi, are you there?
Yeah, I think he's there.
Yes. Yeah.
So what was your question? Why you asked with Professor Sahu sir? I mean, did you ask that are there any adjoint map construction from one space to other space?
No, no. I asked a few questions. So in that, I think what you are referring, if I am getting correctly, I asked that. So Jacobi farms, so Jigel modular farms, they have Fourier Jacobi decomposition.
Correct.
So Jacobi farms are kind of they give local information about Jigel modular farms. So whatever results we are getting by considering Jigel modular farms rank in Cohen bracket.
Okay.
And on the other hand, we have already results for Jacobi farms rank in Cohen bracket. Can we deduce the Jigel modular farm result from Jacobi farms?
I see. Okay.
Yeah.
Okay. I thought that okay. So I'm just a comment here that we know that there are VM operators, right? From the Jacobi form of weight k index 1 to Jigel modular forms, right? Conan actually computed the adjoint of that operator. I mean, from there you can get a map from Jacobi form to Jigel modular form, and Conan actually he has computed the adjoint of that map.
BM map takes Jacobi farm to Jacobi farm with the changing the index, you know.
He meant summation of VM
Summation of VM.
I1.
Summation
So
of VM. Correct.
No, Fourier. I think Fourier Jacobi are talking, no?
yeah, so you take so you take phi 1 and apply VM and take this formal sum. So that is Jigel,
Yeah.
right?
Yeah, but that is what Saito Kurokawa, no? We start with phi 1 and just apply VM and keep and add the formal power series and we get Jigel modular farm.
Yeah, actually you are right.
So, so there is one thing like if you see there is a remark in this where Choi has defined Rankine coin bracket for Jacobi form, so where she says that it is possible to get this Rankine coin bracket for half integral weight from Jacobi form considering theta decomposition. So similarly, in principle, it could be possible to get Rankine coin bracket for Jacobi form from considering Fourier Jacobi expansion of Siegel modular form, but I haven't seen this. It has been done.
Abhas bhaiya,
Yes. So, there is info, I think.
can I share my slide now, or I
Yeah,
should
you can
wait?
share. You can share. You can share. So,
Sorry.
yeah, you can share. You can share. Yeah.
Okay.
So I request Professor Kamdev to chair the next session. Over to you, Kamdev.
Okay, thanks, Abhas. So still 1 minute, I think, to go.
Yes, 1 minute. Yes.
At any point, if I am not audible, please Abhas let me know. So I am worried towards the internet connection. Yeah.
Yes, sure.
Abhas bhaiya,
Yes.
can you see my slides?
Yes, your slide is visible. Yes, fine.
Yeah, so now we can start. I think it's already 4. So welcome to the another afternoon session. And our first speaker of this session is Moni Kumari. She did her PhD from NISER Bhubaneswar and then she joined TIFR Mumbai as a postdoc. Currently, she is a postdoc at Bahrain University, Israel. She works in number theory with a special focus on analytic number theory, modular forms, analytic properties of L functions attached to automorphic forms. Moni, please. And yeah, and today title of our talk is construction of Poincare series by generating kernels.
Thank you, sir, for the introduction. And I also would like to thank the organizers for giving me this opportunity to speak here. So today I'm going to talk about construction of Poincare type series by generating kernels. So the main aim of this talk is to construct a very interesting series, which is basically a function on h cross some complex right half plane. And then we will see that if we consider this series as a function on h, then it will be a square integrable and also will satisfy nice transformation formula. Whereas if we consider as a function in the s variable, then we will prove its meromorphic continuation to the whole complex plane. And the idea to get meromorphic continuation for that series is basically to use the spectral knowledge of the weighted Laplacian. So let's first start with the setup. So gamma, which is a subgroup of PSL2R, is a fusion group of first kind. Then we know that this gamma acts on H via the fraction linear transformation. And we identify the corresponding quotient space by M that we know is a Riemann surface. And in this talk, we are also allowing to have parabolic points on M. So notice that if M does not contain any parabolic point, then M is compact. Further, we denote gamma tilde, which is a subgroup of SL2R, is the cover of gamma. So now I'm going to define multiplier system. So for any real number k, a multiplier system of weight k is a function on gamma tilde such that the value of chi at minus identity is e to the power minus 2 pi ik, and chi is homomorphism up to this factor. And this factor we can write explicitly in terms of exponential. And there is a result that which says that if our space is non-compact, then for any real number k, a multiplier system exists. But this is not the case if our space is compact. Next, I'm going to define a weighted Laplacian. So for any real number k, the corresponding weighted Laplacian that we denote by delta k is given by this expression, which involves delta x, delta y, which are partial derivative with respect to x and y. So generally this delta k acts on the space of twice continuously differentiable function, but we want to study the spectral decomposition of this operator delta k. So for that, I'm going to define a class of automorphic function on which delta k will act. So here hk denote the space of all measurable functions on H such that the value of f at the point gamma z is the same as fz up to this factor. And this factor involves our multiplier system. And the j function is given by this explicit ratio. So here gamma is ABCD, which is an element in the gamma tilde. And f should be also a square integrable over the fundamental domain. Then we know that that Hk is a Hilbert space with respect to this inner product. Okay, now I'm going to see some examples. Sorry. So if G is a cusp form of weight k, then if we define Fz, which is y to the power k gz, then we know that this is an element in Hk for trivial multiplier system. And delta kf, actually f is an eigenfunction for delta k with eigenvalue k into 1 minus k. So in other words, the space Hk is a more general class of automorphic forms than a classical cusp form. So now let me state some fact which says that if f belongs to Hk, which is twice continuously differentiable, then delta kf satisfy the same transformation formula as of f that one can check. but delta kf may not be square integrable. Of course, if our space M is compact, then this is always true, but in general may not be. So because of this, delta k is not an operator on the full hk. Whereas if we define dk, which is the set of all twice continuously differentiable function inside hk, such that delta kf is inside hk, then delta k define an operator from dk to hk. And this operator was studied by Rolk, and he also proved that actually this is an essentially self-adjoint operator. It means one can extend this operator to a self-adjoint operator uniquely. So let me denote that extended operator by delta k tilde, whose domain is dk tilde, which contains dk. So now we know that delta k tilde is a self-adjoint operator. So one can talk about its spectral decomposition, and that is studied by again Rolk. So he proved the following, that if you take any f in dk tilde, then f can be expressed as a linear combination of phi n's, where phi n is a countable orthonormal system of eigenfunction of dk tilde with spectral coefficient inner product of phi n with the given f, plus we have finite sums. Here C gamma is the number of parabolic points inside M, and this sum involves parabolic Eisenstein series that I will define in the next slide on the line half plus it. So notice that if our space is compact, then we don't have this sum, which involves Eisenstein series. Okay. So before going further, let me state some facts about this phi n. So we know that these are eigenfunctions. So let lambda n denotes the corresponding eigenvalues. Then we know that these eigenvalues lies in the interval k into 1 minus k to infinity. In particular, these eigenvalues are real number. And for each lambda n, the multiplicity is finite. It means the corresponding eigenspace are finite dimension vector space over C. Further, if we consider this series 1 over lambda n square, then we also know that this series converges. So as I promised, now I'm going to define parabolic Eisenstein series. So for a given cusp zeta j, k is a real number and chi is a multiplier system, we define the corresponding Eisenstein series that we denote by Ez by this, which is given by this series. And here the generating functions involve our multiplier system, and this is the j function that I have defined in the definition, and into this imaginary part of aj gamma z to the power s. Here aj is a matrix which take the cusp infinity to this given cusp zeta j. This series and its analytic property were studied by Selberg. So he proved that this series Ej is a C infinity function on H cross this complex right half plane. And on this right half plane, this is holomorphic. This is also an eigenfunction for the Laplacian with eigenvalue s into 1 minus s. And one can also prove its meromorphic to the whole complex plane, which says that the only simple pole in this half plane, right half plane, lies in the interval half to 1. And also notice that Ez has no pole on the line real part of x equal to half, and from which it follows that Ez is a continuous function on H cross this line. Okay, so now let me make one remark that this series is a example of a more general objects called Poincare type series that I will define next. And we have also seen in the last slide that it's this extended Eisenstein series on the line half we have used to get the spectral expansion for the Laplacian. So now let me define what is Poincare type series. So a Poincare type series by mean a series of this form, where gamma runs over the group, and here Hs is a function on H, which also depend on the complex parameter whose real part is large enough. And to make sure that this kind of series converges, we should also put some condition on Hx. Now, so once we have this definition, now one can ask the following question. Construct some nice and interesting Poincare type series and study its analytic properties like functional equation, meromorphic continuation, like compute to Fourier coefficient, etc. So in the remaining time, I will give some examples like Selberg and Niebuhr Poincare type series, which are a special kind of Poincare type series, and we will also see why this series are important. It means I will give some of the application of this series, and after that I will state my result. So let's start with the Selberg Poincare series. So if m is a non-negative integer and z is a point in the complex half plane and s belongs to C whose real part is bigger than half, then we defined then actually Selberg defined Pm, which is a function on H cross this half plane, which is given by this series. And the generating functions involve this imaginary part gamma z to the power s e to the power 2 pi I m gamma z, and here gamma runs over the set of representative. Then he proved that if m is non-zero, then this is a square integrable function on gamma mod h. And remember this in our notation, this is h0. It means if we take weight equals to 0, then we have this space. Unlike Poincare type series, this is not an eigenfunction for the weight 0 Laplacian, but this series satisfies this nice recurrence relation. And using this relation, one can get its meromorphic continuation to the whole complex plane. So let's see why this series and its meromorphic continuation is important. So here is the application. So here gamma tilde is a congruent subgroup of SL2G. Then we know that the space L2 gamma H on delta, the weight 0 Laplacian acts on this space. So one can talk about its spectral theory. Let me denote the corresponding discrete spectrum by lambda i's. Then we know that the first, because these are real numbers, so we can write like this. And because our k is 0, so this lambda i's belongs to close interval 0 to infinity. So the first eigenvalue is 0, and for which the corresponding eigenfunction is, one can take the constant function. So it is natural to ask, what is the lower bound for this, the first non-zero coefficient eigenvalues? So in this direction, there is a conjecture due to Selberg, which he given in 1965. We says that this cannot be less than 1 by 4. And as far as I know, like this conjecture is still open in general. In the same year, to us this conjecture, he proved the following, that lambda 1 cannot be less than at least 3 by 16. And to prove this result, he used like previous that Selberg Poincare type series and their meromorphic continuation. So very quickly, let me tell you the idea of the proof. So for that, so for any mn positive integers, consider the corresponding Kloosterman zeta series, whose coefficient involve Kloosterman sum. If we use the trivial bound for this Kloosterman sum, then we know that this series converges in this right half plane. Then using that the previous Poincare series and their meromorphic continuation, he proved the following proposition, which says that if you take sigma naught bigger than half, then this series admits analytic continuation to this half plane. Sorry, Abbas bhaiya?
No, it's okay. Please go ahead.
Okay. Then this series admits analytic continuation to this half plane if and only if lambda 1 is bigger than equals to sigma naught into 1 minus sigma naught. In other words, the reason of convergence of this series gives a lower bound for this lambda 1. Okay, so once we have this result, then if we use the Weil's estimate for the Klusterman sum, which gives that this series is holomorphic in this right half plane, real part of S bigger than 3/4. So if we take in particular, if we take sigma naught equals to 3/4, because we know that in this half plane this series is holomorphic, then the correspond and apply this proposition, then the corresponding lower bound for this lambda 1 is 3/16, and hence this completes the proof. So to get this proposition, he has used that previous Poincare series and their meromorphic continuation, and also the fact that series is inside L2, is a element in the L2 function. So now let's go to the other kind of Poincare type series, which is called Niebuhr Poincare series, which he did introduce in 1973. So if m is a non-zero integer and z is a point in upper half plane, then he defined fm, which is here z was real part of s bigger than 1, again by this series. So here this I function denotes the modified Bessel function of the first kind, and that we know this function grows exponentially. And he proved the following properties about this series, that actually this is a function, fm is function on gamma mod h, because this is invariant under gamma. So like Eisenstein series, this is again this is also an eigen function for the Laplacian with eigenvalue s into 1 minus s. And one can also prove its function equation, which involves this zero with zero Eisenstein series. And from this, one can get its meromorphic continuation to the entire complex plane, and the possible pole of this series located by the eigenvalues of delta and the pole of this Eisenstein series. So now I'm going to give one application of this Eisenstein, this Poincare series. So let's f and g are two Cus forms of weight k for the group SL2G with Fourier coefficient a and bn. If we fix a positive integer m, then Goldfeld in 1979, he considered this generalized shifted series. So here, which involves the Fourier coefficient of a, f, and g, and for b, we have a shift by m. And here f is the Gauss hypergeometric function. Then using the analytic property for Niebuhr Poincare series, he obtained the corresponding analytic properties for this generalized the shifted L series. Okay, so in the remaining time, now I'm going to talk about my results. So there first I will define a new type of Poincare type series, and then I will talk about that one can get its meromorphic continuation to the whole complex plane, and we will also locate the possible poles. So here is the definition of this new Poincare series. We say that if S is a complex number whose real part is sufficiently large. And if we take 2 points in the upper half plane, Z and W, then we define Ks tilde, which is given by this series. So this series involves the multiplier system, cosine hyperbolic function, and this is again the Gauss hypergeometry function. And here this Hk is defined by this. So next, so before going to say anything about its meromorphic continuation, I would like to make one remark that if k equals to 0 and chi is trivial, then this series, this Ks tilde, and its meromorphic continuation is studied by Jorgensen, Anna, and Lala in 2016. In other words, our result generalizes their result for any real weight k and for any multiplier system. And also, let me make one remark that our result is for vector valued forms, like even and multiplier system are also vector valued. But for simplicity, I have stated all the results for like scalar valued. So our result is more general than them. So let me state the first theorem. So which says that if you fix W inside H and S is a complex number whose real part is bigger than 1 and mod k, then as a function in the first variable, this is an element in HK. It means it satisfies nice transformation rule, and which is also square integrable. So one can get its transformation formula by doing simple computation. But to prove square integrability, we have used a result of Hazel. And from there, we prove that this is a square integrable. Now I am going to talk about its meromorphic continuation. So if you fix Z and W, then as a function and in S variable, one can get its meromorphic continuation to the whole complex plane. And the possible pole for this function, here we have multiplied with suitable gamma function, are located at the point half plus minus itj minus 2n. So here n runs over the positive integer, and tj, these are the spectral parameter for the discrete eigenvalues of delta k. And if the space is non-compact, it means if there are cusp in the space, then we have also possible poles, like at the point 1 minus rho minus 2n. So here rho is a pole for the parabolic Eisenstein series, which lie in the interval half to 1. And also at the point rho minus 2n, where again rho is a pole for this Eisenstein series, but in this left half plane. So now let me give you the idea of the proof for this part, for this meromorphic continuation. Okay, so remember we want to get the meromorphic continuation for this function Ks tilde as a function in S. So for that, our first step is using the spectral expansion for the weighted Laplacian. We first construct a distribution called wave distribution that I denote by W, which acts on a nice class of test function. Then we derive sufficient condition on the test function so that the wave distribution W acting on this new class of test function produces an element in that HK. In other words, L2 automorphic kernel. So now if we take this particular test function, which I denote by GS, which is given by the ratio of gamma function and cosine hyperbolic, then we prove that this test function satisfy all the sufficient condition given in the step 2. Hence, if we apply wave distribution on GS, which gives an element in HK because of step 2. So we denote this new function by Ks, which is an element in HK now. So since this new function is an element in HK, so one can talk about a spectral expansion. So then we prove that the corresponding spectral coefficient satisfy a very nice functional equation in the S variable. S goes to S plus alpha for suitable parameter alpha. And because of this functional equation, we prove that this new function can be meromorphically continued to the whole complex plane. So remember, our aim was to prove the meromorphic continuation for this function, Ks tilde. But up to here, we proved that this new function Ks can be meromorphically continued to the whole complex plane. And which is enough because of the following result. So in the last step, we proved that if you take any complex number C, whose real part is bigger than 1 and mod k, then for any Z and W, these two functions are same up to this factor. So once we have this relation, we know that this Ks, this right hand side can be meromorphically continued to the whole complex plane, which gives a meromorphic continuation to this Ks tilde. And hence, one can get the meromorphic continuation for this Ks tilde. And all the possible poles of this comes from this possible pole of this Ks function. And with this, I end my talk. So thank you for the attention.
Okay, thank you, Moni, for nice talk. And now I invite comments, suggestions, doubts. Anyone has any question?
One question.
Yeah.
I want to know that how your work or results which you have derived are related to the work of Ramanujan. In what way they are related? Or are they related?
Yeah, actually here we are working with more general class of like automorphic form, as I have told you at the beginning of the talk. And also,
Since we are celebrating the
yeah, that's true.
birthday of
So,
Ramanujan, and his works must be reflected some way.
so I think if you take a special case of this series, let me go. Okay. Like I have told you that if you take K equals to 0 and some particular this multiplier system, then this will give us some classical cus form or maybe half integral, something related to that, and from there we can see that one can get. So yeah, so maybe for a special case, one can get some result in the classical modular form, and from there we can see that that is related to some kind delta function.
So there is one question in chat box. So maybe Abhishek, so Abhishek, you can ask this. So are the test functions dense in L2 gamma H? L2 gamma slash H?
Yeah. So sorry.
Yeah, no, I was just reading that question. These test functions are dense in L2H mod gamma.
Yeah, like one can say. So basically, the test function that we have taken here are basically generation of compactly supported functions. So yeah, that is the we take.
Is there any more question?
No, I don't see any question in my box.
Thank you, speaker, once again, and we go to the next speaker. Immediately, since it is time for the next start. Okay, Javan, are you there?
Muni, you can stop presenting your screen.
Okay, sure.
Yes. Can you hear?
Yeah, sure.
Okay. So let
Yeah.
me
No,
first.
how to-
Okay. Enter screen or what?
No, yeah, entire screen you can share.
First, share the.
Enter screen.
Yes.
It is not coming. Why?
No, first go to present now.
Yeah, present now I went.
A window, choose that, and then share it.
Enter screen, no?
Yeah, entire screen you can choose. Choose entire screen and then share. Then share.
That is not coming actually. That share is coming, but when I am clicking, it is not.
No. When you share, then you go to your PDF.
Oh, okay. Now I can. Okay, I have. Okay. Let me see. Means like present now. Entire screen. Yeah, entire screen. I don't think that it will work. Let me see. A window.
Share particular window also.
Review. Particular. Okay, maybe share.
No, when you are sharing entire screen, what is it showing?
Not.
Share option is coming or not?
Share option is coming if I choose that.
Yeah, so share it.
Then share, I click, then it says that our Google Chrome might not have screen recording permission on your computer.
Where can you please close and reopen it again?
You give permission and then you cut and then rejoin.
Or give permission means go to system preference, something it is saying.
Yeah. So because I think you are sharing for the first time, that's why it is asking.
Okay, where is that system preference? And where I can.
Now, when you give permission, then you have to leave the meeting and you have to rejoin again.
Okay. That permission thing I'm not getting. That is what I'm saying. Permission, where is that?
If you don't mind, can you share your screen so that? Oh, but that is.
That is not possible. Or I don't know. Let me.
Okay. So
otherwise, what you can do, you can send the slide to me. I can share that slide and you present it. And whenever you want, I can just move it one by one.
No, okay, no. But what I do, this is my laptop. I'm changing it to desktop. Otherwise.
Yeah. Okay.
Okay, you have many things.
So if you are,
let me see.
So if you take class on desktop, then better you can do on that.
Let me. Okay. Let me change. Let me sign out.
Yes, you can leave. Yes. Unmute your mic. Unmute your mic. No, it is not audible.
No. Jaban, unmute your mic.
Yeah. Now
Yeah.
it's fine. Okay.
Yes.
Now you are audible.
Yeah. I thought it will happen, but okay. Now I am opening.
Yes.
Fine.
Yes. Yes.
Now.
Yes. 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 Fine.
Okay.
Yeah. So now we can start, I think. So let me introduce the speaker. So I am happy to introduce the second speaker of this session, Professor Jaban Meher from NISER Bhubaneswar. Jaban completed his PhD from HRI Allahabad. After his PhD, he was postdoc with Professor Ram Murthy at Queen's University, Canada. After that, he joined as Inspire Fellow at IISc Bangalore. And from there, he moved to NISER Bhubaneswar as faculty. He is currently at NISER Bhubaneswar. His work in number theory, specifically modular forms and real functions. And today he will talk on mod P modular forms and simple congruences. Please, Jaban.
Yeah, thank you, Professor Sankadhar. So, thank you. I thank the organizers for inviting me for this day talk, means December 22nd, Ramanujan's birthday. So, my title of the talk is Mod P modular forms and simple congruences. So, we'll see what a simple congruence means. And then means like my talk will see that it is related to Ramanujan. It will come after some time. We have already seen modular form, so I'm not going to define what a modular form is. So MK is the finite dimensional complex vector space of modular forms of weight K on SL2G. So what I am starting is most of my talk I'll do modular forms on SL2G, and after that I'll talk about some of our results which is based on modular forms on congruence subgroup. But most of the part I'll do for SL2G, because what we have done is kind of some except for technicalities, like one can generalize. So so this is MK, and then MKR, if R is a subring of C, then MKR is the set of modular forms with Fourier coefficients in R. So we know that any modular form has Fourier coefficient. So if all those Fourier coefficients in R, so then we say that modular form is in MKR. And we have seen the Eisenstein series also. Eisenstein series, one can define for K bigger than equal to 2, but we know that like for K bigger than equal to 4, this is a modular form, but E2 is not a modular form, which has been said before that it is a quasi-modular form. So in our talk, we will not discuss anything about quasi-modular form, but we will see that E2 plays a very important part in our theory, or mod P theory of modular form. So this is the result actually which generally one studies in a first course in modular form, which has been also stated in one of the lectures, that any modular form, MK is modular forms on SL2G. So any modular form can be written as a polynomial in E4 and E6. So the Eisenstein series E4 and E6. So what we want in this talk, we are interested in the actually Fourier coefficients of modular form. We'll see that if they belong to particular kind of rings, we give some kind of nice structure. And because of this, we'll always whenever we say P is always a prime which is bigger than equal to 5. In some cases, we'll have P equal to 3 also, but that will mention if we take P equal to 3. And ZP is the local ring with the unique maximal ideal PZP. And H, we have seen, like in previous slide, we saw that any modular form can be written as a polynomial in E4 and E6. So that one studies, and this result is also very easily one gets some this result, but this one needs to do some prove one or two result, but they are not very difficult. That it says that what it says, any modular form with Fourier coefficients in ZP can be written as a polynomial in E4 and E6 with coefficients in ZP. Okay, so note that E4, E6 all are coefficient. The E4 has Fourier coefficients, all are integers. Similarly, E6 and ZP. So ZP anyway it contains Z. So this is what. So now what we are going to define is the congruence between two modular forms. So we know that means like if we take two numbers, generally we take integers so that we study the congruence. So here we are kind of like one can generalize this congruence to ZP. Note that Z is contained in ZP. So we are kind of generalizing that congruences between two elements in ZP. So what do we mean by congruences between two modular forms? So we have two modular forms of maybe of different weights, and they have coefficients in ZP. So congruence means always we have to take that the coefficients are in ZP, and we say that F is congruent to G mod P if each coefficient means like An is congruent to Bn mod P ZP for each F. Then we say that F is congruent to G mod P. Okay. So examples, like whenever we define something, we should have examples. Otherwise, there is no meaning. So for any prime P bigger than or equal to 5, we have the following. That means like E2 we know that means like they are the coefficients of E2 are integers. So there is no problem. If it is if coefficients are integers, so they are in ZP. So there is no problem. But what examples we have are EP minus 1 and EP plus 1. So for a fixed P, EP minus 1 and EP plus 1 have all the Fourier coefficients in ZP. And we have some congruences relations also, that EP minus 1 is congruent to 1 mod P and EP plus 1 is congruent to E2 mod P. So here note that EP minus 1 is a modular form of weight P minus 1 and 1 is a modular form of weight 0. So here it says that means like two modular forms, they may be congruent at mod some prime P and they may be of different weights also. This is what we have seen by the example. So what Swinnerton-Dyer proved actually, so this result is the beginning of the mod P theory of modular forms and the periodic theory, what Sayre started, etc. So this is the first result and from which everything started, mod P, periodic theory, etc. So he proved that, like he proved that if we take two modular forms, of course we are looking at congruences, so the coefficients are in ZP. If they are congruent mod P, then there is a relation between their weights. So weights cannot be arbitrary. He proved that weight are congruent modulo P minus 1. So that means they are in the same equivalence class modulo P minus 1. So it cannot be arbitrary. And so actually Swinnerton-Dyer proved much more result, which I'll come to that. But it says that means like mod P, this is the first result of that kind, that if two modular forms are congruent, then the relation between the weights are this. So we will come to the more general result, and from that result actually this result follows. Okay. So for that actually, like we want to see some structure. So for that we define certain things. FP is the usual finite field with P elements, P is always prime number as we have taken bigger than equal to 5. So we have seen that we are considering modular forms with coefficients in ZP. So more generally, we can reduce any Fourier expansion like this or Taylor expansion like this. So if we have A and Qn, then and then A and R in ZP, then we can reduce like this. Reduce means it reduce modulo PZP. So that means then this series becomes an element here, FPQ. So this power series. Okay. So in ZP, if I reduce, then that will be again will be here. This is one thing. Actually, this is what we'll need. And another thing we'll need is that previously I said that in any modular form can be written as polynomial in E4, E6, and also if you have particular like the coefficients should be in ZP, also the coefficients of that polynomial also should be in ZP. That I have stated. So similarly, we kind of define reducing a polynomial mod P. What does this mean? So here reducing a series mod P, and now this is reducing a polynomial mod P. It meaning, so we know that if I have a polynomial xy in two variable, so I can write like this with coefficient C, A, B in ZP. So reducing means again similar way that you reduce the coefficient mod P ZP. So that again becomes an element in FP xy. So what you consider, what we want to do actually, because you have seen that modular forms of different weights may be congruent. So what we do, we take modular forms, coefficients in ZP, collect all those modular forms coefficient in ZP and reduce the coefficient. And then when you reduce the coefficient, that modular form is not again a modular form, but it is some kind of power series with coefficients in FP. So then we want to give a structure kind of thing to all those this set. So that this is what we are trying to see. So MZP is a graded ring of all modular forms on SL2G with all the coefficients in ZP that we take. And MFP, whatever I said, that you take that and then reduce modulo PZP, everything, and then whatever set we get, that is MFP. And this is the result of Swinnerton Dyer, which was the starting point, and he gave a structure of that algebra, FP algebra, MFP, that there is a ring isomorphism between FPXY modulo the ideal generated by this, ideal generated by the A bar XY. I have already defined what do I mean by the reducing a polynomial minus 1. So this is the ideal generated by this and MFP. So where AXY is what? AXY is a polynomial. We know that EP minus 1 is a modular form in modular form of weight P minus 1 on SL2G. So I can write it as a polynomial in E4 and E6. And also I said that the coefficients are in ZP. So that is why the polynomial also will have coefficients in ZP. So that polynomial I am considering. So that polynomial, and then I reduce that polynomial, that is A bar XY. So it says that there is a, okay, sorry. So there is a ring isomorphism between this and MFP. Okay, so now we come to the generalization. So this above result has been generalized in higher level also. So the results by Ketch actually, so he did it for gamma n, for n bigger than equal to 3. So, and this was this beginning of the Ketch modular form, or many more theory on mod P or periodic modular form. And Bennett Gross, he did it for gamma 1n, n bigger than equal to 4. And both the results, actually, the proofs were actually geometric in nature. So if you see, that means level for 2, n equal to 2 is not done for any of these things. So we consider the case of gamma 02. This is a joint work with Sujit Kumar Prue. So we generalize this result for modular function gamma 02. I do not know, because gamma 1 and Gross has done. I do not know, and we didn't find any reference also where anything is known about gamma 0n or anything like that. So these are the references. Gamma n Cage is done, and then Gross gamma 1, and then we thought of doing for level 2, and then we have done it for gamma 02. And our proof is mostly we follow the Swinnerton diagram. So possibly that nobody looked at after the result of Cage and Gross, otherwise anybody could have done, looks like. So for that actually we, if you look at the results of Swinnerton diagram, that is the one result which is more important, which I stated, is that any modular form with polynomial, any modular form with Fourier coefficients in ZP is a polynomial in E4 and E6 with coefficients in ZP. So that kind of thing one need. Like in case of SL2G, we have E4, E6 generate this thing. So similar kind of thing here also we have for gamma 02, which is the modular forms which will replace E4 and E6 in gamma 02 will be E22, E22, first one is E22, which is defined in this way. E2, we know that it's not a modular form, this is a quasi-modular form, but this combination if you take E2, E2, 2Z minus E2Z, so this is a modular form of weight 2 on gamma 02. So this is one thing, and the other one, I'll come to this, but in general, so this is weight 2 modular form on gamma 02, and for any k bigger than or equal to 4 even, so the Eisenstein series corresponding to the cusp infinity. So note that in SL2G case there was only one cusp infinity, but here gamma 02 we have two cusps. So corresponding to two cusps we have two linearly independent Eisenstein series. We don't go into the other kind of thing which we do not need here. So the Eisenstein series, So the Eisenstein series corresponding to the cusp infinity is given in this way. So again, this is a problem actually. So it should be EK, not E2. So there is a mistake here. So here I did this thing. So it should be EK and EK here. So then this is the Eisenstein series of weight K corresponding to the cusp infinity. So this is the result which we want, like in case of SL2G. Here also, this any modular form on gamma 02 can be expressed as a polynomial in E22 and E42. Okay, so this is what we stated for SL2G, and here also similar thing happens. And note that E22, E42 have Fourier coefficients, integer Fourier coefficients. And similar thing, like if we take coefficients in ZP, actually here we can take P equal to 3 also. P equal to 3 also. In gamma 02 case, we can take P equal to 3 also, and that will work. In SL2G case, we took P equal to, like it worked only for P bigger than or equal to 5, but here P equal to 3 also, this will work. So this is the result we proved. We proved similar result, but here we take P bigger than or equal to 3. That means we include the case P equal to 3 also. And we proved similar kind of isomorphism. Like M gamma 02 FP is similarly we consider the all Fourier expansion and the reduced mod FP, and that set we consider. And FP and the AXY is the same thing, but little modification, that AXY in ZPXY is a polynomial, so polynomial will be different because P minus 1, if you look at for P bigger than or equal to 5, EP minus 1, this is a modular form of weight P minus 1 in SL2G, on SL2G. So then naturally it becomes a modular form on gamma 02. So if it is in gamma 02, then again it can be written as polynomial in E22, E42 by our previous result, and here the coefficients are in ZP. So similarly, one can have this, and if it is p bigger than equal to 5, and this is just E22 if p equal to 3. Okay, so this is the AXY. AXY is this. So similar result we have proved for gamma 02. So now we come to some applications of this kind of result. So already people have studied the application. So we begin with the Ramanujan congruences. Ramanujan studied this kind of congruences in the morning first lecture. Professor already gave some history of this kind of brief history of the partition functions and Ramanujan how he discovered. So here we have the congruences, well-known congruences for partition functions, and it is also known from the work of Algebra and Boylan that there is no other prime for which a congruence of the above form is true for the partition function. We know that for higher power of this also there are certain kind of congruences, but the prime remains same 5, 7, 11, but not other primes of this kind of congruence. So these kind of congruences has a name. So in modern language they are called simple congruences or Ramanujan type congruences. So what is a simple congruence? Whatever we saw, what Ramanujan discovered, a similar way we define that. We say that this is a simple congruence at C modulo P if A Pn plus C is congruent to 0 mod P. Okay, any Lorentz series like this has a simple congruence at C modulo P if A Pn plus C is congruent to 0 mod P for all n. So this is how, like if you look at the Ramanujan congruences, which Ramanujan started, the Ramanujan discovered for partition function, then they are the simple congruences associated to the series this, the generating series for the partition function Pn. So the question is, like modular form also, it has a Fourier expansion or Q series expansion. So we can study the simple congruences for modular form. So what is the relation? Because partition function, if you take the generating series, this can be viewed as a kind of, this has some relation to modular form. So up to some particular term, it is a modular form of weight minus half kind of. So then we can talk about the congruences, similar kind of simple congruences for other modular forms. And this was actually studied by Michael Dewar, and he proved that he considered this kind of modular form. Of course, this is not a modular form, E2 power R, E4 power S, E6 power T, but this can be like thought of as modular form, because you have already studied, I have already stated that EP plus 1 is congruent to E2 mod P. So what we are looking at is that congruence mod P. So you can replace E2 by EP plus 1. EP plus 1 power R you can take, and then because you are looking at congruences, so this will be the same thing. So he studied this kind of modular form, like congruences, simple congruences for this kind of modular forms, and he proved that if it has a simple congruence, then it has to, the prime P has to satisfy certain bound. Like for example, if you consider E2, E4, E6 are ST integers, and then R bigger than equal to 0 and not all 0. If all 0, then you'll get only 1. So if that is the case, then P has some bound in terms of R, S and T. Okay. And we also get some, there in that paper also they Michael Dewar gave some examples also of simple congruences. That means it says that, in other words, it says that if P is bigger than this, then you cannot get simple congruences. So this gives a criteria for non-existence of simple congruences. So similar, and he used the mod P theory, already known, SL2G, Swinnerton Dyer had done. So those theory Michael Dewar has used to prove this result. So we then again applied whatever we did for gamma 02 to get a similar kind of result in case of gamma 02. That means we considered here, so we similar result means E4 E6 has been replaced by E22 E42 natural way, because E4 E6 they are generated is modular forms on SL2G. Here E22 E42 generate modular function gamma 02. And we have proved similar result, that we have also proved the non-existence of simple congruences for P bigger than something. And that means we have, if it has simple congruence, then P has to satisfy certain bound. And also we give some examples. Of course, there are some trivial kind of examples, but we give some non-trivial examples of simple congruences. That means P less than equal to this, and then we have a simple congruence that we have proved. Okay, so this is the end of my talk.
Yeah. So if anyone has question, please go ahead. Any question? Jaban, I have just one quick question. Yeah. So we are not doing for any gamma zero and arbitrary. We don't have corresponding E22 type series.
I couldn't get.
Can you put your mic?
Yes.
Yes, yes.
Yeah, Jaban. So just I asked that we are not doing for any gamma zero, and since we have Eisenstein series like E22 in that case.
No, I'm still not getting again echo. Some your voice is getting echo.
Okay, no problem. Ask your
No,
mic.
Me like two mic. Now you can.
Yeah. So just quick question that gamma zero n we are not considering since we don't have E22 corresponding series for gamma zero n.
Gamma n.
Yeah,
Gamma 0 n.
You considered gamma 02. So gamma n was by cards, gamma 1n gross, and then you are considering now gamma 02. So
Yes.
I am asking, we are not considering general gamma 0n, any label gamma 0n, since we don't have the corresponding E22 type Eisenstein series in that case, or what? What is missing?
We are considering means what? Means like not considering means what sense you are saying? What we are not considering? Means like
So what you proved it is for gamma 02.
Yeah, gamma 02 means like we could use the idea whatever the Swinnerton Dyer has done. Actually.
Yeah.
There are only two generators.
There are two generators. That is, that is one thing actually. That is one thing we have used in some places like the structure theorem actually. So there we have used at some point, because if you look at the structure theorem, it says that some modulo something is isomorphic to that. So that means you have to that kernel. That means you give an isomorphism, and then that is subjective, and then kernel is that if you prove, then that gives you isomorphism. So that is how. So then to prove that that is the kernel actually. So it is clear that is already contained in the kernel. That is true. That whatever this quotient thing already contained in the kernel. But to prove that exactly that is the kernel, we use that it is generated by true. Actually, because we use some kind of dimension, kind of commutative algebra. That means like prime. What is the dimension called? That the chain of prime ideals, etc.
Cruel dimension.
Cruel dimension. So that cruel dimension we use to see that means like that is exactly the kernel.
Okay. 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 Anyone else has any question to Jaban? If not, let's thank the speaker once again. And we move to the next speaker. Professor Ips Martin. I can see he is already there. Hello, Ips.
Hi, can you hear me?
Yeah, sure. So
perfect.
How are you?
Thank you. Fine, thank you. I'm very happy to be part of this conference. I'm very far in space and time, but I'm really happy to be part of this celebration of Ramanujan's birthday, and I thank the organizer for the invitation.
Okay, it's so thanks for accepting the invitation. And are you going to give talk by sharing the slides? How?
Yeah, let me see. Should I do something or just a presentation now, right?
Yeah. Can you share your slide on this Google Meet?
Can you see anything?
Not now.
Okay, so what I should do? Go to present now, right?
Yes.
Go to inside the screen and then share.
Then
You choose a window. First, you go to present now, and if you click on now
Yeah, it is coming.
yeah.
Now you can see my screen, right? Or
no, if you go to slide, please click on slide.
Click on the slide. Click on the slide.
Okay, hold on for a second. Now,
yeah.
Can you see something?
Yes.
Yes, visible.
Yes, it is visible.
It is visible. Perfect. Okay, so I would like to talk about integral kernel for a generalized Kegemas series. Okay, so
let me introduce the speaker formally, and then we start the talk. So it's my pleasure to introduce our next speaker, Professor Yves Martin. He did his PhD from University of California, Santa Cruz. After his PhD, he was postdoc at Concordia University and CRM Montreal, Canada. Currently, he is professor at Universidad de Chile, Santiago, Chile, which is very old university in Chile. His area of research is specifically analytic aspects of automorphic forms, especially modular forms, Jiggle modular forms, Jacobi forms. So now I invite Professor Yves Martin to deliver his talk on an integral kernel for a generalized Kaiser-Mass series. Professor Yves Martin, please.
Thank you very much. As I said, I'm very happy to be part of this conference. And this time I would like to talk about a paper that is already a year old, since it's not my last work, but it's about an object that I think one can do more about. So let me introduce, first of all, the general setting, and then I will tell you about this integral kernel, which is sort of the goal of this research. So first, I will introduce some notation, okay? The symplectic group of degree n is gamma n, and I recall is the set of integral matrices of size 2n by 2n, such that A transpose C, B transpose D are symmetric matrices, and A transpose D minus C transpose B is the identity matrix. Here, every time that I write A, B, C, D, it means blocks of size n by n, defining this matrix M in the symplectic group. This group acts on this complex analytic manifold that is a generalization of the complex upper half plane, consisting of the n by n complex matrices Z, which are symmetric, and such that its imaginary part, which is a n by n real symmetric matrix, has a quadratic form, is positive definite. So on this complex analytic manifold, the action of the group is the one that is in the screen. Z goes to AC plus B times CZ plus D inverse. So this is just obviously a generalization of the Möbius transformation on the complex upper half plane. Okay, this group also acts on a vector space of holomorphic functions. Namely, if you have an holomorphic function f from Hn to C, then it sends f to another function that I will denote f slash km, which is the same function f, but evaluated at mc, multiplied by the number determinant of z plus d to the minus k. Of course, then there's an action for every integer k, which in our case, we don't lose much generality if we think is a even integer, actually an even positive integer. Of course, this is a generalization of what happened in the case n equal to 1, which is the case of classical modular forms on the complex upper half plane. In particular, in this talk, we're only interested in the case n equal to 2. And as I said, n equal to 1 is the classical elliptic modular form case. Okay, we have here a group, an action on Hn, the Siegel space Hn, and an action on functions f on Hn. Now, we can define the space of Yk Siegel cusp forms over the group gamma n, which we call S sub k of n, as a set of holomorphic functions on the Siegel space Hn, such that are invariant under the action of the group. So f slash k of m is equal to f. And they have the Fourier expansion given here. So f of c is a sum of complex numbers c of t, the Fourier coefficients, and an exponential function, e to the 2 pi I trace of tz. Okay, and the index of this infinite sum is T, which is a real n by n matrix, symmetric, half integral, and positive definite. Half integral means integers in the diagonal entries and half integral in the off diagonal matrix, off diagonal entries of T. Okay, so this is our primary object of study, the Siegel cusp forms over actually gamma 2, degree 2 Siegel cusp forms. And to each of them, we will associate the Kegemas-Dirichlet series. This is a Dirichlet series in one complex variable W, which if it has real part large enough, defines a holomorphic function, and is defined as a series of the coefficient Ct times the determinant of t to the minus w. And there's a number epsilon t, which is just the following. On the set of indices, J2 acts gamma 1, which is SL2C. And the action is given by T goes to G transpose TG. So epsilon T is just a normalizing factor, which is the number of elements in the group, which fix T. Okay, this is a very classical object that associates to a Siegel cusp form of degree 2, a Kegemas, a Dirichlet series of this type. Okay, of course, here the analogy is the L function of an elliptic modular form defined with its Fourier coefficients. Okay, such a Dirichlet series has nice analytic properties if you multiply with some suitable gamma factors. Here, gamma is the Euler's gamma function, and if you multiply the Dirichlet series by these gamma factors, you know, for example, you can prove that this new series has holomorphic continuation to the whole complex plane, and satisfies some functional equations. Okay, so let's go back to the space of vector space of Cas forms of weight k degree 2 Siegel Cas forms. It has an inner product, the Peterson inner product, which is the integral over the quotient H2 quotient by the group gamma 2 of this expression f of c, the conjugate of g of c, and determinant of the imaginary part of c to the k minus 3 and dx dy. The integrand is invariant under the action of the slash operator, so it makes sense to integrate on a fundamental domain for this action. And our vector space, which is a finite dimensional vector space over the complex numbers, is a Hilbert space. Okay. Then let's look at the following situation. This is a very, this is just a linear algebra situation. There's nothing special and it's very simple. If you have a linear map from the vector space to the field, so a linear map from SK2 to C, which takes any Cas form, and you go to the number that you get when you take the Dirichlet series at F, evaluated at W naught for a fixed complex number W naught, then this linear map, because of this basic linear algebra thing and this Risch theorem in great generality, can be represented by an inner product. This means that there must be some unique Cas form in SK2, which I denote omega W0, such that the map, the image of F can be obtained as the inner product of these special Cas forms omega and F. Actually, for technical reasons, I just have to put F star, which is the conjugate of F evaluated at minus the conjugate of C. But essentially, the only thing I'm saying is that the linear functional can be written as the inner product of F against this particular Cas form. So this means that you can get the image of the linear map by integration with a kernel. And this kernel is this special Siegel modular form omega. Okay. Then the question is, what is omega? Conan and Sengupta obtained an explicit description of such an omega, and it's some gamma factor, which are not very important now, this dw, and they describe it as a sum over the group of the function 1 over the determinant of z to the w slash m, where m runs over the group mod some subgroup. So the point is, it's a sum of a very simple function, determinant of w to the minus w, sorry, determinant of z to the minus w slash the action of the group. And actually, the result that they got was for Siegel Cas forms of any degree. Okay, and it's very similar. And of course, this is just a generalization of something that was already known for degree 1, where the Dirichlet series is the usual L function of Cas form F, and the explicit description of this omega was first given by Henry Cohen for integers w between 0 and k minus 2, and studied with detail by Diamantis and O'Sullivan for any w in the complex numbers. And again, of course, they get some special gamma factors times 1 over tau to the w slash g, where g goes through the whole group. Okay. Now, this is the Dirichlet series. As you can see, it's quite possible that for different t's in the index set, the coefficient ct is different, but the determinant of t is the same. So there is some collapsing of information. So it's not clear that in this Dirichlet series you get a faithful representation of all the information that is in the Fourier coefficient of the Siegel-Cas form. So one can do something better, and that's it's replace the function determinant of t to the minus w for another map, and that is what one calls the power function. So this take any C 2 by 2 matrix and takes the determinant and raise it to the W as before, but now you take the 1, 1 entry, the upper left corner, and you raise that to a different complex variable S. And so now you consider this more elaborate Dirichlet series in 2 complex variables, which is a factor, the Riemann zeta function, that doesn't matter. Then the same coefficient than before with this normalizing factor and some determinant that is not important. But now you take the power function at minus S minus W. And this gamma 1 infinity is just the stabilizer of infinity in gamma 1. Okay. This new series converges in some region, real part of S bigger than 1, and 2 times real part of W bigger than K plus 3 minus real part of S. And clearly, it has more information than the Kegemas series in the sense that separate in a better way the information that comes from the Fourier coefficients. And as before, if you multiply this new Dirichlet series in 2 variables with some suitable gamma factors, then you get nice analytic properties for this new Dirichlet series. It has meromorphic continuation to the whole C2 space and satisfies 2 functional equations. This lambda fs w is the same that lambda f of 1 minus s w and lambda f of s k minus w. Okay. And now let me play the same game that I mentioned before. You fix S naught W naught in C2, where lambda f of S naught W2 makes sense, and define the linear functional that takes any Cas form f and go to this special value of the lambda Dirichlet series. And that gives you a linear function, and therefore there is a unique omega S naught W naught, which is a Cas form in the space of Siegel-Cas forms, such that this value is obtained as omega against f star for any f Cas form of degree 2 weight k. And as before, the problem is to describe this Siegel-Cas form omega. So that's the goal. Okay, so that's the candidate. As you see, it's very similar to what Conant and Gupta obtained, but we replace determinant of C to the minus w by this more complicated function p, the power function to the minus s minus w, and that one we take the action of the elements in the group slash km, where m runs on gamma 2 mod some particular subgroup. This new object is what we are looking for. First of all, you can show that makes sense on some place in the d naught in the space of c squared, okay? And the theorem is the following. If k is bigger or equal than 12, remember it's an even integer, and you introduce these two objects, which are very simple. This is the completed Riemann zeta function and a polynomial in S. Now, if you multiply this with this new object that I just introduced, this omega, you can see that in principle, this was makes sense this in some region of C2, but now it admits a holomorphic continuation to the full space C2 cross H2. Okay, so we have a well-defined function on this full set. And more importantly, satisfies two functional equations. W go to k minus s minus w, s is the same, and sw goes to 1 minus s, and s plus w minus 1/2. So it has these nice analytic properties, holomorphic continuation, functional equation, and also for any s and w is a Cache form of yk degree 2, which satisfies what we want, namely the inner product of this with any f star actually, is some product of gamma functions, and the value of d, the Dirichlet series in two variables of f, at s and, well, not w, but something very similar. So that's the main result. So we got a good description of what we are looking for, right? We want to find, that's the problem here, to find the properties and description of omega. And that's the result. If you take this omega, then that's what you're looking for. And you know the analytic continuation, the functional equation, and that it does what we want. So in the rest of this talk, I would like to give a sketch of the proof. Actually, if you go to the paper, you will see that there is a lot of technical information. There's many lemmas and many precision that one must make sure that work. But the main idea behind this argument is very simple. So I want to give you an idea of what this what's the main ideas behind the proof. And everything is easier if one introduces this gamma 1 Einstein series in two variables. Okay, here you have some factor, exponential factor. Don't look at this. It's not very special. It's not very important. But you have a sum over gamma 1s over SL2C mod the stabilizer of infinity of the power function of y, iy actually, under the action of the element in gamma 1. This series is important because, well, it makes sense for real part of S large enough, because it allows us to write the two main ingredients in this proof using this Einstein series. The Dirichlet series in two variables can be written as the Riemann zeta function times this series times the Einstein series at T, the index matrix for the Fourier coefficients, okay? and T runs from, well, on the set of indices under the action of gamma 1 on this quotient. So here we have a description of the Dirichlet series in two variables using the Eisenstein series for GL1, for gamma 1. And the other ingredient is this omega function. So this omega function times some gamma factors that are not important here. So that expression can be written using this Eisenstein series 2. So it's a double sum, and the inner sum is this Eisenstein series E times some exponential, and all this expression slash some elements in the group M. Okay, and this M runs over the group gamma 2, as the C and D runs over the possible second rows of those matrices. This is very classical. It's already in lecture notes of mass, but the point is that we're using these sums over MCD in order to describe this object that we just introduced, this omega function. Okay, now it's not obvious from what I have said, but this Eisenstein series is very simple. It's essentially determinant of y to the minus w times and the Epstein zeta function, which is a very classical object. So that's why it's convenient to work with this Eisenstein series, because we know a lot about it, since we know much about the Epstein zeta function. So using properties of this Epstein zeta function is that we can get information about E, and therefore about, from this expression above, about omega. Okay, now in order to get this sum in here, we had to do some technical step that may be worth to mention by itself. In order to get this, the first identity, we have to generalize Lipschitz summation formula, which is the one that I give here. If you take tau in the complex upper half plane and you translate that by b, any integer b, and you take this expression, you can write it as a Fourier series. And the coefficients are the function power to the w minus 1, and you raise n, where n runs over the integers, times some gamma factors. Well, the same thing you can do with the power function, namely the sum of the power function of C in the Siegel space, translate by any 2x2 integral matrix B, has a Fourier series and is equal to the power function evaluated at some particular powers that now depend on S and W of T and this conjugation and the exponential factor. So this is a generalization of this Lipschitz summation formula, which in the case of simpler case of determinant of C plus B to the minus W, because it's something of one complex variable, was done by Siegel a long time ago. But if you do more or less the same argument, but with the power function instead of determinant, you get this expression. And this expression, as I said, is key in order to get the first identity, the one on top of the page. Okay, now how we can go about to prove the properties of omega. As I said before, this omega where it is here. This omega makes sense on this region. Real part of S bigger than 1, real part of W bigger than 3, and real part of 2S plus W less than K minus 3. You prove this by using this expression that is here, some bounds on the epsilon zeta function, therefore on E, and you get the region that I mentioned before, right? So that region, if you look at its projection to the real parts, is exactly this. So if you take this zero, the region where the omega converges, and you take the real part of S and real part of W, this is the region, this is the, say, the base of the region where omega makes sense. And we would like to have the full plane, right? Because if we want to have the extension, the analytic continuation to the full C2 for W and S, we need to have this extended to the full plane. Okay, so in order to do that, one makes something very formal, which is take this special W tilde, this matrix, which is has blocks, and the block W is this 0, -1, 1, 0. And just by manipulating this expression, this average over the group gamma 2, you can see that omega SW is the same that omega in S K minus S minus W. And the idea and the point here is that this D0 region, this red region before, transform and this change of coordinates into this new region, D1. That if you go to the real part of S and real part of W plane, looks like this blue region now. So you are extending the definition of omega using this functional equation, and now that you know that makes sense on this, the union of these two regions, the blue and the red. And now you do more stuff. Remember that we have this first expression, this gamma factors times omega equal to this sum over this second row CD and this Einstein series with the exponential. Okay, if you manipulate this a bit more, you can write it with some gamma factors, different ones, and you get an expression has an infinite sum of the Poincare series in SK2. And so you can write what you are interested in as this infinite series is infinite sum of Poincare series with coefficients, the Einstein series E evaluated at S and minus S minus W plus 3/2. This in particular tell you that you are looking at a Siegel-Cass form, right? Because this is a combination of Poincare series. I'm not giving the definition here, but these are very classical Cass forms. And now that you have a new representation for this omega function, you know that this new series makes sense on a different region, because you can get an upper bound on the Einstein series, on the Poincare series. You can do some technical stuff to get an upper bound for the terms in this infinite sum, and you get that the full series, namely this omega represented in this way, now makes sense on this green region. So now you know that this omega function that you are defining makes sense on this, the union of all these regions drawn in this picture. But remember that we have a functional equation, right, for omega. And this transformation of the values of the coordinates for the green region give you this brown region. So the transformation SW go to S, K minus S minus W, take you from G2, this green region, to the brown region. So now you know that omega makes sense on all these expression here, in all these in the union of all these regions. But that's not enough. So now that we have this expression for omega as a sum, infinite sum of Poincare series, you use that E satisfy a functional equation. Okay, after all, it's the Epstein zeta function. So satisfy a functional equation, and that takes SW to 1 minus S plus W minus 1/2. The second functional equation is the theorem. And therefore, you already have two functional equations for omega, and that means that you can define omega in the images of the regions that you had before under this new transformation of coordinates. And since S goes to 1 minus S, you can define new regions. You can define this omega function in these new regions. For example, the green region goes to the region defined by these inequalities, and the brown region goes to a region defined by these inequalities, and similarly for the blue region. So if you want to see a picture, here you see that the brown goes to the brown, blue to the blue, green to the green. So this allows you to define this omega function in the union of these other regions where the real part of S is less than 0. But notice that this is not enough, because it means that you have these functions defined on these regions, but in principle, the one on the left are may not be, I mean, since the set are not connected in principle, well, are not connected for sure, it's not clear that that is an analytic continuation of the same function. Maybe there is no way to glue together this function in these two different regions. So one has to do a bit more, and this is the most technical part in the paper, because you have to do a delicate analysis of the Epstein zeta function in order to extend the definition of omega in an holomorphic way to some region that goes from real part of S bigger than 1, which is the brown, blue, and green regions on the right-hand side, to the brown, blue, green region with real part of S less than 0, which are on the left. And you can do this by this analysis that I told you on the Epstein zeta function, which means the Eisenstein series. And that says that omega admits an analytic continuation to the region in red. Okay. And now you are almost done, because now you know that omega, first of all, satisfies two functional equations. You define it in that way. And it's an holomorphic function on all complex numbers SW, such that the real part fall onto some of these regions, the union of the brown, blue, green, and red regions of the plane. But since you have that, you can use this very classical theorem in the theory of several complex variables. If you have any function from some set C in C2, which is holomorphic, and this domain is essentially an open set in R2, and you times this imaginary part, these imaginary lines IR times IR. In other words, if C is a tube with base O, and this O is a connected set, then this function, which in principle is defined only on C, on the tube C, now admits a holomorphic continuation to the convex hull of C. But in our case, our function G is this omega with some gamma factors. The base O is the picture that I showed you before, the union of all the regions with colors that I showed you before. And it's not difficult to see that in such a case, the convex hull of such a tube is C2. Therefore, this omega function admits the holomorphic continuation to the full space C2. And of course, the variable C in the Siegel space is not problem by this expression as an infinite sum of Poincare series. So that's the proof. That's the idea of the proof. So essentially, as you can see, it's just different efforts to represent the function that you are interested to, this omega, into different shapes. And each of them give you some region of convergence, some region where it's well-defined and holomorphic. And then you use this final theorem that give you something more, namely the holomorphicity on the convex hull of the domain that you have. So that's the end of the proof. So I have a couple of minutes left. Let me just finish with the following. So let me just recall what we just proved again. We just proved this theorem. This omega admits a holomorphic continuation to the full C2 cross H2. Satisfy these two functional equations. And is the kernel of this integral given by the Peterson inner product in order to give you this two variable Dirichlet series D, which is a generalization of the Kegel mass. So we proved that, and we finish with three remarks. Okay. These Dirichlet series in two variables are interesting because in a different paper, a most recent paper, I proved that if you have two cusp forms such that this Dirichlet series has function of S and W are equal in some region where real part of S is large enough and real part of W is large enough, then they must be the same. So somehow it's saying that this Dirichlet series in two complex variables really have all the information given by the Fourier coefficients of F and G. It doesn't collapse information. So I don't know if this is true with the Kegel mass series. It could be, but in principle, it's not so clear because, as I said, the Kegel mass series collapses information. So one could imagine that maybe some two different cusp forms have the equal Kegel mass series, but that I'm not so sure. The second remark is that the two functional equations that I give you for the omega function generate a group of symmetries isomorphic to the D4, the dihedral group of 8 elements. And finally, Fernando Herrera which is a student of mine and is finishing in a couple of months, has done the same result that I already presented for cast forms of degree 3. Now it's more complicated because you have 3 complex variables, and the group of symmetries is isomorphic to the dihedral group of order 12, D6. So technically, it's much more involved. Okay, that's it. Thank you very much.
Thank you very much, Ips, for such a Abhas.
Yes.
Sorry.
Okay. So please go ahead with your questions, comments, suggestions, anything. Any question from anybody? Yeah, Ips, I have
Yes.
I have a couple of questions. So as you said that this Kesar mass series, even as you were remarking anyway, so this DFW, whatever Kesar mass series, it may be even trivially zero for non-zero jiggle modular form, isn't it?
Could be. I'm not so. I don't think so, but I'm not so. But yeah, in principle, but
Yeah,
but I'm not so sure. I don't think so, but I don't know.
But do you know anywhere such non-vanishing has been proved? Since it seems for DFSW, you need 2 variables to do that.
Sorry, for the if I remember well, for the KGMA series with just one complex variable, there's some non-vanishing result.
Okay.
Yes,
Yeah,
by Kohnen and Soumya Das, I think.
Probably, yes.
But I think that is in the sense of using kernel function and saying that there exists one Hecke eigenform such that the value will be non-zero on a given point, something like that. In that sense,
Could be. I don't remember, but could be that in average there are at least one single modular form such that this Dirichlet series in one variable does not vanishes. Now, for the 2 variable one, I guess that you can get something similar because you specialize one of the, say, the S variable to 0, and you get the Keje mass. So in that sense, you get you get something. I mean, for free, you get that there are non-vanishing for this series too.
Yeah.
But I don't know if it's something more precise than that.
Yeah. But that doesn't make sure that Kesar mass series of any jiggle cusp form cannot be trivially zero. I think that will not make sure that.
No, it's not so. Right. On the other hand, I believe that if you allow real part of S or real part of W large enough, actually, the last remark that the first remark I give you probably shows that, because if you have F different than 0, and you take the Dirichlet series in 2 variables large enough, with real part of S and real part of W large enough, if both of them are 0, then the cast form has to be 0.
Yeah, but in that result, we are using 2 variables, S and W. So in both,
I believe that also for one variable you can do the same, but you have to say that both of them. I mean, the non-vanishing thing is for some precise S in some particular region. But if you are not concerned with that, then you allow S with any real part, then if F is non-zero, the Dirichlet series is non-zero too, somewhere. Yeah.
Okay. Yeah, okay. Maybe I will look at that carefully. Means just from two
Surely.
variable to one variable can I deduce? Yeah.
Yeah.
Okay. And this whatever construction we did, this omega SW of Z, this which is now which you proved entire in an electric continuation in C2 cross H2. So this appears somewhere else as well. This as kernel function somewhere else also be used.
This omega function, you mean?
Yes, since it generalizes the Conant's and Gupta series, isn't it? Kernel function.
Exactly. And you can use it, for example, to get proof of properties of this Dirichlet series. So has an application. You get the properties of omega, and therefore you can deduce the properties of the Dirichlet series D, SW. And if you take the special value of our omega in two variables, you get as a special case for some particular specialization, you get the omega found by Conant and Sengupta. But more uses of this cast form, no, I don't have. In particular, one could try to get the Fourier expansion of this, the Fourier coefficients of this omega. But I don't know, it may be a very cumbersome computation. I'm not so sure. In fact, what I believe is true is that the same thing must be also holds for any degree n. So we already have it for degree 2, degree 3, and I'm sure that must be true for any degree. But then the problem is that you will have a very complicated and messy computations because already in degree 3, the group of symmetries is much larger. So instead of 2 functional equations, you will have 3. So probably for n, you will have n functional equations. And now this picture that I show you in the real part of S cross real part of W will be something, I don't know, with 9 variables, with n variables or so. So it will be much more complicated to get all these regions to adapt to something such that you get a convex hull equal to the C to the N.
Yes, sure. Yeah. Okay, so anyone else has any question? If not, let's thank the speaker once again. And thank you very much for joining us. And yeah.
Thank you very much. Thank you very much, Karam. And I'm very happy that I gave this talk.
Yeah, sure. We are also very happy to listen your talk. And now we will move to, I think, Abhas. Next session is contribute session.
Yes.
That will start at 6, I think. Is it?
Yes. Yeah. So yeah, thank you, Professor Sangh, for chairing this session. Now, next session is for contributed talks, and I'll request Professor Balesh Kumar to chair this session. Balesh, over to you.
Yeah, thank you, Dr. Abbas. So I am sorry that my camera, I don't have a camera in my desktop, so I is speaking. No picture. So I think first speaker is Dr. Sujit Kumar.
Okay, so shall I start sharing?
Yes. So, Dr. Sujit, can you please share
Yeah,
so
I'm sharing.
we can start on time?
Let me. It's not coming actually. Wait. I think I have to join again.
Just, yeah, there is present now.
Yeah.
Okay, probably he'll join again, then we can start.
Yes.
Yes, Sujit, unmute your mic and then share your screen. Yes, Sujit, share your screen. Go to present now.
Actually, there is some problem. Chrome wants to share the content of your screen. Okay.
Okay, so allow.
Allow and share. Yeah.
Yes.
Now coming.
So is it? Are you able to see that slides?
Go to your slides. Go to your slides. Your
Okay.
slide.
Now it is coming.
No. Open your slides.
Yeah, I have opened my slides.
But and click on that. Click on that.
Yeah. Okay, let me share again. I think I should open this again.
Yes.
Yes. Go to full screen. Go to view. Yes. Then full screen. Yes. Yeah, perfect.
Okay, so should we start, Dr. Abhas?
Yes, sure. Go ahead. We are already.
Okay, so welcome to the evening session of the today's conference. And the first speaker in this evening session is Dr. Sujit Kumar Singh from ISER Bhopal. So he will be talking about congruences in Hermitian-Jacobi forms over imaginary quadratic field. Dr. Sujit, please, over to you.
Sujit. Unmute your mic.
Yeah, Dr. Sujit, please, unmute your mic. I think you are not audible. Yeah, now it is okay.
Okay. So I would like to thank the organizer for giving me the opportunity to speak here. And I will be speaking on congruences in Hermitian-Jacobi form over QI. So let's start from modular form. So by H we will be denoting the upper complex upper half plane. and we give the definition of modular form for SL2G. So any function from H to C is said to be a modular form if it satisfies these two properties. The first one is a modularity condition, and that second, it has a Fourier expansion of this form. So throughout the slides, I will be using this notation. So by MKSL2G, we denote the vector space of all modular forms of weight K. And if we take the Fourier coefficient in some ring R to be subset of C, so we will denote the collection of all those modular forms which have all their Fourier coefficients in the ring R by this notation. So these are the two standard example of modular forms. So the first is Einstein series. So Einstein series for k greater than 2 equals to 2 is defined by this, and for k greater than equals to 4, these are modular forms. And Ramanujan delta function is also modular form of weight 12, and it's a first cusp form, and it is given by this result. So okay, so next is we define modular form modulo P. So as Dr. Javan defined in his slides, that how we define the two modular form to be congruent. So similarly we define here. So first throughout we will be fixing the prime to be greater than equals to 5, and Zp to be the localization of Z at the prime ideal Pz. Suppose we have two modular form f and g, which has Fourier expansion given by this way. So we say that f and g are congruent modulo p if their corresponding coefficient are congruent modulo pzp. So their pzp is the unique maximal ideal in zp. So we drop the notation pzp and only simply write it as mod p. Okay. So this is the result by Senator Dyer. So he stated that if we have two modular form and they are congruent modulo p, then their weight must be divisible by p minus. Weight difference is divisible by p minus 1. And next, so there are two modular forms which have, as stated by Dr. Javans, there can be two modular forms which are congruent modulo p. So it's natural to define to know the smallest weight which can be congruent to a modular form. So we define filtration. Suppose f is any function which has a Fourier expansion, and if f is congruent to some modular form g, so we define the filtration of f to be the infimum of all the weights of modular form which are congruent to f modulo p. So using this definition, we can see these examples that EP minus 1 is congruent to 1 mod p, and EP plus 1 is congruent to E2 mod p. So these congruence can be found using Kumar congruence and von Stott congruence. So if we want to calculate the filtration of EP minus 1, then it is congruent to 1 modulo p, and 1 is a weight 0 modular form, so its filtration is 0. And other thing is that E2 is congruent to EP plus 1, but E2 is not a modular form, but we can calculate its filtration because it is congruent to a modular form. So the filtration of E2 will be P plus 1. Next, we define theta operator. So theta operator, suppose we have any modular form which has a Fourier expansion. So if we apply this theta operator on this f, then it also has a Fourier expansion given by this. So it has a Fourier expansion, but it does not satisfy the modularity condition. So theta f is not a modular form. But Senator Dyer proved that suppose we have a modular form f, then there exists a modular form of weight k plus p plus 1 such that this theta f is congruent to g mod p. So now we can see that theta f is congruent to some modular form. So it's natural that we can calculate its filtration. So he also proved that filtration of theta f is always less than equals to filtration of f plus p plus 1. And this is equal if p does not divide the filtration of f. Okay. So yeah, so next is we define UP congruence. So suppose we have any Fourier expansion modular form that we say take modular form. So we define the UP operator on f by AFN q to the power n. So here we take out those coefficient AFN such that P divides n. And we say that F has UP congruence if F slash UP is congruent to 0 modulo P. So these are some example of UP congruence. So Ramanujan delta function, as we have seen, so this delta slash UP is congruent to 0 mod P, and this was proved by Ramanujan for primes 2, 3, 5, 7. So it comes from Ramanujan congruence that delta P is tau P is congruent to 0 mod P for these many primes, and since delta is a Hecke eigenform, so we can get the UP congruence also. And next, in 1972, Newman proved that for P equals to 2411, this is again delta slash UP is congruent to 0 mod P. And recently in 2010, for this prime, it has been proved. And also he proved that these are the only primes for P less than 10 to the power 10 such that delta slash UP is congruent to 0 mod P. So Ono uses these two results, this result and this result, these two results, and the Tet cycle of theta operator to prove that we can give an equivalent condition for the existence of UP congruence. So suppose that F is any modular form and prime P is greater than K, then it says that F has a UP congruence if the filtration of this element is equals to P minus K plus 3. So we shall see this by an example that how it works. So suppose we take F equals to delta and P equals to prime 13, then F delta slash by this here from here you can see that delta slash U13 is congruent to 0 mod P if its filtration of this element is P minus K plus 3. So that is 4. So if you calculate this, so then it is 4. And this thing means 13 minus 12 plus 1, then it is delta is 2. So it says that it has U13 congruence if the filtration of this is equals to 4. But the only modular form of weight 4 is E4. So this thing says that theta square delta is congruent to alpha E4 for some alpha belonging to ZP. So, but it cannot happen because this side constant term is 0. So, it is not possible that theta square delta is congruent to 0 mod alpha E4. So, from here we can directly see that delta has no U13 congruence. So, it's for small primes, this is really very useful to see that it has a UP congruence or not. But for big primes, it's not very easy from this formula also because dimension will increase. That here we are getting only 4, so K equals to 4. But if you go higher primes, then it will be a large number of things will occur. That here we will not get nice thing. Okay, so now this congruence has been generalized to Jacobi form with matrix index and Ziegel form of any degree by Martin Raum and Olive Character in 2015. And they used this nice result. They proved that suppose if I is any Jacobi form, so here M is any symmetric positive definite half integral matrix, and we denote by JKM gamma L ZP the Jacobi form of weight K with matrix index M and Fourier coefficient ZP. So they prove that if phi is any Jacobi form, and then phi can be written like this way, and where Fi are modular form and phi are some Jacobi form, and suppose psi is any other Jacobi form, then also we can write this by this, and if these two are congruent, then corresponding Fi's are Fi and Gi are congruent mod P. So it reduces to modular form, and from there they extract those property and prove the similar result as we have Uno's result in the case of Ziegel modular form and Jacobi form with matrix index. So we have proved this UP congruence in the case of Hermitian Jacobi form. So first I will define what is Hermitian Jacobi form. So Hermitian Jacobi form for over Qi is defined by this. It's a function from h cross c square to c, and it has a modularity condition that it satisfies this thing. And second, that lattice transformation, and third is that it has a Fourier expansion given by this. So yeah, so we will be following this notation. So SJKM delta gamma jo, the space of Hermitian-Jacobi forms of weight k index m parity delta. And when we take Fourier coefficient in R, then we do not treat by this. So we have proved that similar to result of modular form, we have proved that if phi and psi are two Hermitian-Jacobi form of weight k and k dash, and if they are congruent mod p, then we have proved that these indices must be equal, and k and k dash, they are congruent to mod p minus 1. So now to prove this result, we have uses some mapping from Hermitian-Jacobi form to classical Jacobi form, and using those mapping from the result of Martin Raum and Olive character, we have proved this result in the case of Hermitian-Jacobi form. And next, so we defined the filtration in the case of Hermitian-Jacobi form. So suppose we have any function from h cross c square to c, and it has a Fourier extension of this way, this form. And if phi is congruent to some modular form, then we define filtration to be infimum of all the weights of modular form which are congruent to phi mod p. So yeah, so similar to Jacob modular form, we have a heat operator in here. So it is given by this, and if we have a Hermitian-Jacobi form, if we apply this LM operator here, then it has a Fourier expansion given by this way. So it comes out 4 Nm minus norm of R square. Okay, norm of R. Then we needed to, similar to the result of Sonata-Dyer, we needed to prove this result, that if phi is Hermitian-Jacobi form, then it should be congruent to some modular form of weight. If we apply LM operator, then it should be congruent to some Hermitian-Jacobi form of weight k plus p plus 1. And this result was proved by Olive character and a student of Olive character in 2050 for a Hermitian-Jacobi form for index m equals to 1. And using this result, they have proved the UP congruence for index m equals to 1. And the main thing which required to prove this result is the structure result, as we have discussed in the case of Jacobi form. So they first proved the similar result of that kind in the case of Hermitian-Jacobi form with index m equals to 1, but they couldn't prove it for m greater than 1. So we have proved for m greater than 1. So what we use, so we take the different, we have taken a bigger space. So we have defined a Jacobi form for SL2G semi-direct product O square, and we have seen that it has everything similar to Hermitian-Jacobi form with epsilon equals to 1, and this Hermitian-Jacobi form is a subset of this bigger space. And next we have proved that this space is isomorphic to Jacobi form with matrix index with m equals to this thing and L equals to 2. And using this, we have extracted the structure result to the case of this here. And also we have proved that if we denote the filtration in this space by this, so we have, and if phi is any Hermitian-Jacobi form, so we have proved that these two filtration of phi is equals to filtration of with respect to Hermitian-Jacobi form, and filtration of Lm phi is of n equals to filtration with respect to this space. And using this, we have easily proved the required result what we needed. And then using these two results, we have proved the UP congruence. So first we defined UP congruence. So similar to the case of modular form, suppose we have a Fourier Hermitian-Jacobi form which has a Fourier extension given by this. So we defined phi slash UP to be this. So we take out those coefficients C phi and R such that P divide 4 Nm minus R. So we say that phi has UP congruence if phi slash UP is congruent to 0 mod P. So using those two results, we have proved that suppose phi is any Hermitian-Jacobi form, it has UP congruence, then we have proved that its filtration of this element must be equals to P plus phi minus K. Okay. So these are my some references, and so the results are from this paper, and thank you.
Okay, thank you very much for Dr. Sujit for giving such a nice talk. And so any question or comment? If there are no more questions, so let us thank the speaker once again. And the next speaker is Dr. Lalit Vaish. And Dr. Lalit, can you please?
No, Lalit.
Oh,
Lalit
Lalit,
Vaish.
still your defense is pending. Okay.
No, even not thesis. Means
Submitted.
not, even
Okay,
not
okay.
synopsis.
Okay, Mr. Lalit. Yeah,
Yes.
please share your screen and then.
Bales, just 1 minute. Hello.
Click on the slide. Click on the slides. Lalit, click on the
Yeah,
slide.
just click
No,
there. Yeah.
yes, yes. Now full go
Slide
to.
is not showing.
No, it is showing. Just go back. Just click on the slide. Yes. Now go full
Okay,
screen.
okay.
Yes.
So is it visual?
Yes, yes.
Okay, thank you, Dr. Bales.
Okay, so just 1 minute. Can you go to the first page or?
Sorry. Yes.
Okay, so the second speaker of the evening session is Mr. Lalit Vaish from Harishchandra Research Institute. So he will be talking about sign change of Fourier coefficients of Hecke eigenform at primitive binary quadratic form of fixed negative discriminant. Yeah,
Okay.
Mr. Lalit.
Yes, thank you, Dr. Bales. First, I would like to thank organizer, especially Abbas Biaf, to give me opportunity to talk in this work conference. So my title of the talk is sign change of the Fourier coefficient of Hecke eigenform at the primitive binary quadratic form of fixed negative discriminant. So in this way, I will talk about the Banerjee and Pandey's work, and then at the end I will explain what I have done in my work. So I'll explain the brief history and then Manish and Banerjee's work and some key ingredients of the proof. And at the end, I will explain our work. So sign change of Fourier coefficients of the cusp form is an interesting problem which has been studied by many peoples. And there are many quantitative results which has been uh, given for the number of he has counted means many people have counted the number of sign changes, and the problems becomes difficult when one consider the sign change for subsequences. So first, Professor Ram Murthy have obtained the sign change property for the subsequences at the prime numbers. So first of all, let f is a normalized Hecke eigenform having this Fourier series expansion. So here this lambda fn is known as is called the normalized Fourier coefficient of f. So in 2013, Knopp, Conan, and Dickinson shows that if the Fourier coefficients of if the lambda fn's are real, then they have infinitely many sign changes. So in the same year, Jaban Meher, Kashi Vishwanath, and Karamdev have studied the sign change problem for subsequence lambda f n to the power j for j equal to 2, 3, and 4. And in 2014, Conan and Martin have proved that the Fourier coefficient at the subsequence lambda f p to the jn has infinitely many sign changes for almost all the primes. So recently in 2020, Banerjee and Pandey have obtained the sign change for the Fourier coefficients of the cusp form at the sum of two squares. So he proved that if k is even integer and f is a normalized Hecke eigenform of the weight k for the full modular group, then the sequence lambda f supported at this sum of two squares, then the sequence has infinitely many sign changes. So he proved that in the interval x to 2x, the subsequence changes at least x to the 1 over 8 minus 2 epsilon times in that interval. So we'll explain little brief preliminaries. So let Sk SL2Z denotes the space of cusp form of weight k for the full modular group, and this let F is an element of this Sk SL2Z having this Fourier series expansion lambda fn into the k minus 1 by 2. So this f, we say that this is a normalized Hecke eigenform if the first coefficient lambda f1 is 1, and in literature this lambda fn is known as a normalized nth Fourier coefficient of f. So this lambda fn satisfied this Hecke relations lambda fn, lambda fm and lambda fn is sum over divisors over gcd of mn, lambda f mn by d squares. So if gcd is 1, then this is lambda fn is equal to lambda fm is equal to lambda f of mn. So it says that this lambda fn is a multiplicative function, and this lambda fn satisfies the Delink's bound, which says that hello, okay, lambda fn satisfied this Delink's bound, which says that lambda fn is bounded by this number of divisors of n, which is less than n to the epsilon for any epsilon. So now we write this sum of two squares by q, and this R2n denotes the number of representation of x, number of representation as a number of representation of n as a sum of two squares, and the generating function for R2n is given by, we denote by theta q, which is defined as a summing over all the pair of integral points in z2 q to qx, which is given by this r2n q to the n. And we know that this theta q is nothing but theta q square, which is the usual theta function, which is defined as a sum over n q to the n square, and this is a half integral weight modular form for the congruent subgroup gamma 04 n gamma 04. And since it is a square, since theta q is a square of theta, so it is a weight 1 modular form for this congruent subgroup gamma 04 with this discrete character chi minus 4. And this R2n also satisfied this Weil's bound, and the formula for R2n given explicitly in terms of this Jacobi symbol defined as a x d over x sub d, d is equal to this Jacobi symbol d by d, and it is given by this R2n is 4 times the sum over the divisors chi minus 4 d. So if one wants to consider the behavior of sign chains, then one need to consider the following sums s1 and this s2. So s1 is given by this lambda f of this qx, where this qx is a sum of two squares, and we have to consider up to x, and this s2 is nothing but the square of this lambda f qx. So if we write this qx as a n, then this is nothing but how this lambda fn, how many times it occurs. So s1 becomes this lambda fn r2n, and s2 becomes the square of lambda fn and r2n. So it is enough to find this upper bound for s1 and the approximate behavior of s2 to study the sign change property of this subsequence. So what Manish have proved, that he shows that this s1 is bounded above by x to the power 3 by 4 plus epsilon, and s2 is approximately cx times cx plus big O of x to the power 3 by 4. So cx is coming because of the L function have the pole at s equal to 1, and this c is the residue at s equal to 1. So to prove this proposition, uh, we first define this the L function associated to this associated to this coefficients lambda f and r2n. So we define this r f theta qs is sum over n lambda f and r2n divided by n to the s. So this is nothing but this Rankine-Selberg L function. This is related to Rankine-Selberg L function of f and theta square. And we define another function rs, which is given by lambda fn square r2n divided over n to the s. So he decomposed this rs in terms of this known L function, this Rankine-Selberg of f with itself, and twisted by this character chi minus 4. So he proved that he proved this lemma which decomposes rs in terms of this known L functions. And after this, to prove this proposition s1 s2, so we need the truncated parents formula, which relates this Dirichlet series with its partial sum. So once we need This parents formula says that this partial sum is related with some integral of the Dirichlet series. And after that, we need this convexity bound for this Rankine-Selberg function Rf theta q, which says that if f is a normalized Hecke eigenform and theta q is theta square, then for a fixed sigma in a 1 by 2 plus epsilon to 1 plus epsilon, we have this bound, which says that this absolute value of this Rf theta q sigma plus it is 3 plus mod t over 2 to the power 1 minus sigma plus epsilon. So sigma, so s is a sigma plus it and epsilon is any positive real number. So and we need one more result of this K Matsumoto, which is for the integral estimates for this Rankine-Selberg L function. So which says that if f is a normalized Hecke eigenform, then for a fixed sigma we have these integrals. So to prove this, the estimates for this S1 and S2, we'll apply this truncated parents formula. So since this lambda fn satisfied this Ramanujan Delink's bound, so for a given epsilon we can choose n to the epsilon by 6, and R2n is big O of n to the epsilon by 3, and this is because of Welles bound. So the coefficients appearing in S1 is an which is lambda fn R2n. So it's satisfied big O of n to the epsilon by 2, and this lambda fn square R2n satisfied this big O of n to the 2 epsilon by 3. So for S1 and S2 we can apply this truncated parents formula, which relates with its L function. So then what will we do? We shift the line of integral from 1 plus epsilon to 1 by 2 plus epsilon, and then apply the convexity bounds and this integral estimates to obtain these estimates for S1 and S2. So to prove the sign change result, we need the following lemma, which is due to Murthy and Meher. So he says that if an is a sequence of real number and it satisfied the following three condition, which says that an is a big O of n to the alpha, and the partial sum up to x of an is big O of x to the beta, and the square of the an's summing over n up to x is c times big O of x to the gamma, then choose a number delta which is bigger than this alpha plus beta and gamma. Then this an has at least one sign change in this interval x to x plus x to the delta, and in the interval x to 2x there is a x to the 1 minus delta sign changes. So since this S1 is big O of 3 by 4 plus epsilon and S2 is Cx plus big O of 3 by 4 plus epsilon, and this lambda f and R2n satisfied this big O of n to the epsilon, so we can choose the number delta. Manish and Banerjee have chosen this 7 by 8, so which is bigger than this 3 by 4 plus 2 epsilon. So in the interval x to x plus 7 by 8, there is at least one sign change for this subsequence. So we generalize this result for quadratic form, binary quadratic form, which have the if q is a binary quadratic form and it has some fixed discriminant. So corresponding to the discriminant, if the class number is 1. So we have considered the sequences of binary quadratic form which have the discriminant and having the class number 1. So we prove the following result, that if f is a Hecke eigenform, and since we are considering in SKSL2, so we need not assume that the coefficients are real. So if you go in level, then we need to assume that the coefficients are real. So the sequence lambda f qx has infinitely many sign changes, and moreover we can improve this 7 by 8, sorry, x by 1, x2 and 1 over 8 minus 2 epsilon to 1 over 5. Because we can choose any number bigger than 3 by 4. So we also improve, so here is the list of the discriminant which have the class number 1. So minus 3, minus 4, minus 7, minus 11, minus 19, 27. So this minus 4 corresponds to the sum of two squares. So these are the fundamental discriminant, and there are the non-fundamental discriminant for which the class number is also 1. So we improve these results and obtain we have refined this delta, which we have got this x to the 8 over 33. So these are references which I have used to work out on these results.
Okay, thank you very much, Mr. Lalit, for the talk. And so, any question or comment? So, if there are no question or comment, let us thank Mr. Lalit for the talk. And the next speaker is Mr. Rishabh. And Mr. Rishabh, can you please share your screen and then we can start.
Okay, भैया. Yeah, it is visible. Hello.
Yes.
Okay.
So should we start?
Yeah.
You can start. Go ahead.
Okay. So welcome to the next lecture of evening session, and the lecture is by Mr. Rishabh Agnihotri from Harishchandra Research Institute. He will be talking on the Fourier coefficients of certain Hilbert modular forms. Mr. Rishabh, take over to you.
Okay. Thank you, Dr. Balesh Bhaiya. And first, I would like to thank Dr. Abhas Kumar Jha and his team for organizing this conference and giving me such a opportunity to present my work. So, what I'm going to present work with Professor Kalyan Chakravarti. So, title of my talk is on the Fourier coefficient of certain Hilbert modular forms. So this is the plan of my talk. First, we introduce some definition, and then we motivate towards our problem. After that, we go to the proof of the theorem. Yeah. So let me start by some definitions. Let k and n be are positive integers. Let gamma n not be a subgroup of SL2G defined as this. And so a modular form is a holomorphic function defined on upper half plane. A holomorphic function is said to be of weight k and label n if it satisfies the following kind of properties. First one is about it has a nice transformation property, and second one is some technical condition that it is holomorphic at cusps. So if vanishes at all cusps, then we say that such form is a cusp form. Yeah, from above we see that our function is periodic by putting some suitable values, and a function is periodic and holomorphic, so it has a Fourier series expansion. So this is the Fourier series expansion of f. Here AFMs are the known as the Fourier coefficients of f, and yeah. So the set of all modular forms of given fixed weight and label forms a vector space. We denote this space by mkn, and skn is denotes the vector space of cusp form inside mkn. One of the classical problem in the determination of modular form by a subset of Fourier coefficients. So can one determine the modular form by a proper subset of Fourier coefficients? So in this direction, the most talked about result is Sturm bound, which says that we need only finitely many coefficients which must determine the modular forms. So this is the result that we have to take this up to the Fourier coefficient up to the lambda kn, where lambda is some positive constant. So suppose all Fourier coefficient up to lambda kn are 0, then f is 0. In other words, we can put this like as, suppose we have two forms and up to lambda kn both have same Fourier coefficients, then f and g must be same. A similar question can be asked about how many square-free Fourier coefficients are required to determine the modular forms. So for classical modular form, the answer of this question is given by Professor Soumya Das and Pramath NMB, and they get an upper bound So first they used the prime number theorem for associated L functions, and they get upper bound, which was has a upper bound in exponential nature. So later they improved this upper bound by using Rankin-Selberg L function for primitive cusp forms. So this is the precise theorem of Professor Somedas and NMB. So here they take let n be a positive integer and chi be a Dirichlet character with conductor m chi, and the condition is that n divided by m chi is a square free. So suppose you have a form inside sk n chi which is non-zero, then for any epsilon positive there exists a square free coefficient in between with this bound, such that this square free coefficient is going to be non-zero. So we consider the analogous problem for Hilbert-Marlowe forms. So yeah, to state our theorem in the case of Hilbert-Marlowe form, we need to define the notion of Hilbert-Marlowe form and its lifting to the idyllic setting. So let F be a totally real field of degree n over Q, where Q is the field of rational numbers. OF is the set of ring of integers. Let H denotes the narrow class number of F, and let Ti be the complete set of representative of narrow class group of F. So corresponding to each representative and fix an integral ideal n, we have some subgroups, congruent subgroups inside GL2F. This is the namely subgroup where OF is our different ideal. So now we are going to fix some multi-index notation. So let's suppose K is a member of Z plus N. That means all are greater or equal to 0, and Z belongs to Cn. And for a scalar inside complex plane, we write Z power K is nothing but a product of their corresponding coefficients. And gamma of Z, where gamma is gamma function, K naught here is a maximum of K1, K2, Kn tuple, and AK is nothing but A raised to the power summation of Kj. Yeah. So definition. So now we are going to define classical Hilbert-Marlowe form. A classical Hilbert-Marlowe form of weight K on gamma I eta congruent subgroup with the label eta is a holomorphic function from upper half plane, n copy of upper half plane to complex plane, and it satisfies some nice transformation property like as our usual classical Marlowe form satisfied. So here we are using multi-index notation, and it satisfies for all matrix inside gamma I eta. So the space of such forms of weight K and label eta is denoted by mk gamma I eta. Yeah. So here we don't need the condition of holomorphicity at the cusp. If F does not equal to Q, then by Quecher principle, automatically we have that if it is holomorphic on Hn, then it must be holomorphic at each cusps. Yeah. So like classical Marlowe form, Hilbert-Marlowe form also possesses a Fourier expansion, which is given by this, and here Xi has totally positive elements. Okay. So we have here for each representative of class group, there is a corresponding congruent subgroup, and we have Marlowe form. So now we are going to associate H tuple of classical Hilbert-Marlowe form to an idyllic Hilbert cusp form, and so the association, and this F must F be a automorphic form on GL2AF, where AF is a ideal ring of F. So the space of idyllic Hilbert cusp form of weight K and label eta will denoted by SK eta. Yeah. So here is the how we associate from H tuple to an idyllic cusp form. This is by namely this equation. So here is M is an integral ideal, and these are the Fourier coefficient we are associated with this. Yeah. So yes, next. So let F be a non-zero Hilbert cusp form of weight K, and label is a square free label. Now we are going to state our theorem in the case of Hilbert-Marlowe form. So let f be as above. That means we fixed here label eta and which is square free, and CMF are Fourier coefficient. Then there exists a square free integral ideal in that range such that CMF must be 0, where f is non-zero is what modulo form, and implied constant depends only on epsilon and f. Clearly this is a generalization of theorem 1. If we put n is equal to 1, we get our usual theorem for classical modulo form, which was proved by Professor Soumya Das and Pramath. Okay, so this is it. So now we are going to talk about the proof of the theorem. Before we go to the proof of theorem, we collect some ingredient so that which helpful to prove our main theorem. So let f and g are two primitive cusp form in SK. Consider the following Dirichlet series. This is namely known as the convolution of f and g. And the second Dirichlet series is we are collecting Fourier coefficients which are indexed by integral ideal which are co-prime to the label eta. And third Dirichlet series is that we are collecting only square free coefficients. So here H denotes that we are taking only square free integral ideals. So we have these three Dirichlet series in our hand. Now I'm going to talk about the relation between these three Dirichlet series. Yeah, so we have following relation between the above defined Dirichlet series. So first this means here the Fourier coefficients are co-prime to the label, and so this is related by to our usual Rankine-Selberg convolution of f and g by this thing. And where and for second for square free coefficients we relate it to the usual L eta by this, where fs and gs are true Dirichlet series, and the property is that they are convergent for real s greater than half. And here Rankine-Selberg convolution is convergent for real s greater than 1. Now we are going to talk about the analytic continuation of our Rankine-Selberg convolution. So this denotes the infinity part of this one, and take capital lambda as f tensor g denoted by this. Then this function has an analytic continuation. So Simra proved the result about the analytic continuation of Rankine-Selberg. So this result says that this capital lambda SF tensor G admits an analytic continuation to whole C whenever f does not equal to G. If f is equal to G, then it possesses at most two poles, which are precisely at s is equal to 1 and at s is equal to 0. And he also calculated the residue at s is equal to 1, which is given by this thing. Yeah. So to prove our main theorem, we proved a fundamental result, so which is that means this is the base of proof of our theorem. So here what we did, we proved this theorem for primitive cusp form f and g, and we want to prove our result for any cusp form, non-zero cusp form. So idea of the proof is that we use new form theory to write any form in terms of new forms. So this result will help us to prove our theorem. Yeah. So now I'm going to the section where we proved our main theorem. Okay. So to prove our main theorem by new form theory, we can write our modulo form summation sum of new forms, where alpha iq are some complex number and bq is operator, lift operator. Yeah. So yeah. So here fi aiq is 0 if fi is not equal to not a new form of label n by q. We consider here bq operator. That's right. And now we choose a q naught, an integral ideal, with the property that it has minimum norm, with the property that corresponding Fourier coefficient is going to be non-zero. So this is the choice of q naught. So now we will compare from equation 4 the coefficient which are indexed by the integral ideal q naught m. And here we are taking m which are co-prime to the level n. Yeah. So on comparing both sides, we have this thing. So note that by choice that any ideal if has norm less than norm of Q naught, then corresponding Fourier coefficient is going to be 0. So we can rearrange above sum, and this sum will become like this. And we define S is nothing but sum of Fourier coefficients, sum of square of Fourier coefficients, and where the H denotes that we are taking sum over square free integral ideal, and also that ideal co-prime to the level, co-prime to the level, co-prime to the level. So now we just rewrite that above one, and we separate the diagonal part and non-diagonal part. Now we can apply our theorem fundamental result to, because here each are new forms, CFI are new forms. On applying the theorem 4, we get such things. Now using Cauchy-Schwarz inequality and dimension, upper bound of dimension on SK eta naught, we get this thing. And since the above equation is independent of the choice of function f, here f is a function which is a compactly supported and bounded function. So this equation is independent of choice of f. So we choose now suitable f so that following conditions hold. So this is this thing, and we will get the result after saying that from above, if the right hand side is positive, then left hand side must be positive, because this is bigger quantity. And on comparing both sides, we will get whenever x is going to be bigger than that, we will get that LHS is positive. So that means we up to range x, where x less than k naught power n, and norm k naught power 3n, and norm n over q naught power 6n square plus some epsilon factor. Within this range, we will get some Fourier coefficient which is indexed by square free integral ideal and which is non-zero. So this completes the proof of our theorem. So here is some references. Yeah, thank you.
Okay, thank you, Risha, for the nice talk. So are there any question or comment? So if there are no question or comment, let us thank the speaker once again. And next speaker is Mr. Kaustav Banerjee. So, Kaustav, are you ready?
Yes. Yes.
Okay, so can you please share your screen? Just you go to there is something called present now in below.
Yes.
Then you click and just share your entire screen.
Mm-hmm. Okay, just let me check. Okay. Ah. Oh. Oh, it says I can't share the screen. Is there any problem? It says I can't share screen. Is there any problem?
It is so. What is it? Do you see entire screen option?
Yes.
Then share.
I do, and then it says that you grant permission in order to. You must grant permissions in order to share screen share.
So you allow.
Just you click there. Yeah.
Allow. It's because probably you are using Google Meet for the first time. That's why it's saying.
So, okay, I'm just checking. It again says that can't share your screen. What should I do? It says only the dismiss options.
Okay, so if it is not, then maybe you can send the PDF to me. I'll share, and then we can.
Yes.
Okay, can I mail it to you?
Yeah, sure. Maybe you can mail it to
Thanks.
Batas also. I mean, you just mail it to me.
Okay.
Yeah, you mail to Dr. Abhas. He will
Yeah.
share your screen and you can speak.
Okay. Thank you. I'm just okay. Okay. Okay, I just sent you an email, Professor Abhas.
Yes.
In Gmail.
Okay, in Gmail.
In Gmail. Sorry, iitbhu.ac.in in the iitbhu. Yes.
I'm just looking for it. Yes, I have got.
Okay, thank you.
Yes, I'm just sharing it. Looking down. Okay, maybe I'll just wait. I'll just go allow.
Yes.
Yes. So can you see?
Yes.
Yes. I think because I have just opened in browser only. So I think it is okay, right?
Yes.
Yeah. So okay. So Bales, please start.
So, Kausto, are you ready?
Yes.
Yeah, so welcome to the next lecture of evening session. So the next speaker is Kausto Banerjee from RISK JKU Linz, and he will be talking on Will-Chen's conjecture on partition inequalities. Mr. Kausto, over to you.
Thank you, Professor Bande, for your kind introduction. I'd like to thank the organizers for organizing this beautiful conference on this auspicious day on the 133rd birth anniversary of Srinivasa Ramanujan and giving me this opportunity to talk here. So my talk title is Will-Chen's conjecture on partition inequalities, and we saw in today's talk, in Professor Awadi's talk, that what is called combinatorial analysis started by Major McMahon. I will go to that, but before, what Will-Chen recently, Professor Will-Chen started the conjecture of partition inequalities. So how we can estimate the partition inequalities on terms of several situations, and how they emerges and how they evolve and what are their consequences. So now I will jump over to the next slide. That says that what is the definitions of partitions. But before going to that, the Leibniz was the first person in the literature, seems to be the first person in the literature who asked in a letter in 1674 to Johann Bernoulli, the guide of Leonhard Euler, in the what sense that Johann Bernoulli about the diversions of integers. So in modern sense, what is a diversion means? Diversion means that how many ways a positive integer can be partitions, can be write as a sum of its in terms of another positive integer. So in formal definitions, a partition of a positive integer n is a weakly decreasing sequence of positive integers whose sum is n. For n equals 0, it's the empty partition. So conventionally p0 is 1, and for example, p of 5 is 7. I chose p of 5 because Ramanujan's congruence p 7n plus 5 is congruent to 0 mod 5, 0 mod 7. So we can write 5 in terms of 7. And then now the question is, what is the growth of Pn? So the growth of Pn, because if I write the table of partitions, then it grows its dynamic is quite chaotic. So what is a McMahon? What Major McMahon in 1916 compute a table that also Professor already said, from 1 to 200 by means of the recurrence formula, this 1 minus x square in the parenthesis, this thing is actually the Euler's pentagonal number formula. And the right hand side I wrote that equals to 1 times that the thing is times by n running from 0 to infinity Pn x to the n. Why this is 1? Because these partition functions of x to the n is actually product of n running from 1 to infinity, 1 divided by 1 minus x to the n. So if I multiply these two, then this is 1, and then if we from here, if I take x to the n, if n is strictly greater than 1, then this power is equating both sides, it has to be 0. So from there you can get that the recursions of partitions, and using that recursions, Major McMahon obtained that P of 200 almost nearly this 4 trillion, huge number. Now we jump over to the, then what is the growth of, yes, so for the growth of partitions, and 2 years later, the monumental breakthrough of the two greatest minds in mathematics, greatest mathematicians there, Hardy and Ramanujan, that the partitions of n is asymptotics to 1 divided by 4n square root 3 e power pi times square root of 2n divided by 3 as n tends to infinity. Now asymptotics, I didn't define it here for giving it, but I am saying that if n any functions is asymptotic to gn as n tends to infinity, that means defined to be limit n tends to infinity fn quotient gn is equals to 1. That means their growth is quite similar, not exactly similar, but quite similar to that. Now, why this partition functions growth is important? Because this is one of the most central problem in number theory, in additive number theory, counting additive functions, and how these functions behave. So, as we saw in they use the celebrating circle method, employing the celebrating circle method to prove this inequality, to prove these asymptotics. And then this enumeration, these asymptotics leads to a completions by Hans Rademacher, the famous analytic number theorist of that century. Their project was during 1936 to 1939, during 3 years, that two papers Rademacher wrote for, we define mu n to be pi by 6 square root of 24n minus 1. So Rademacher wrote a beautiful formula for by suitably choosing the contour in complex plane on the unit circle, unit disk, so that Pn to be this convergent infinite series, and square root of 12 by whatever this. Here in the formula I didn't define two things, that what is akn there and R2 of nn there. So akn is just a Kloosterman sum, and R2 of nn is just the remainder term for the rest of the series, remainder term. Now, in order to grade how we can use this analytic and combinatory analysis to get the from which bound, what in some sense how we could bound these functions. We have the asymptotics, but how we could explicitly bound from which point on these functions behaves how. Then Lemmer did the job, that he bounds akn, the Kloosterman sum, in the more tight way. That means akn is bound, he bounds by akn, the Kloosterman sum, 2 times k to the power 5 by 6, and the remainder term by infinite integrals. So he bounded this thing, and bounding R2 of nn, there is one thing also there. So because in partitions, enumeration of partitions, there is modified Bessel functions of fractional order of 3 by 2 appears. So he bounded all those estimates, and then he found this nice bound of absolute value of R2 of nn is strictly less than this quantity. Now this thing is useful because if I can choose, I am free to choose n running from 1 to any integer so as to get close to Pn. But I will skip for now that. I will come back to this formula later, where how this bounding is important. So now I will jump over to my next slide. So in the literature, in combinatorics, for a sequence of real numbers, it's called log concave or satisfies Turan inequalities. Turan was the first person supposed to be studied this type of inequalities for combinatorial sequences. So if for n greater or equal to 1, a square n minus an minus 1 times an plus 1, this difference is positive. So now in 2010, in the next slide, in 2010, formal power series and algebraic combinatorics conference, Bill Chen conjectured that partition function is actually log concave. for n greater or equal to 26 in his talk entitled Recent Developments on Log Concavity and Q Log Concavity of combinatorial polynomials. But it's 5 years later, De Salvo and Park settled this conjecture that Pn is actually log concave n greater or equal to 26. But Bilchin not only interested in that inequality, but he also tried to estimate that what is p square of n minus pn minus 1 times pn plus 1 greater or equal to 0 means p square n divided by pn plus 1 times pn minus 1 is greater or equal to 1. So I can bound it by lower bound 1. So now what is its upper bound? So its upper bound that first Bilchin obtained 1 plus 1 by n. But later De Salvo and Park make the more precision, and it's the optimal that is written in the red color, that 1 plus pi divided by square root of 24 n to the power 3 by 2. So we can improve the constant, but n to the power 3 by 2 you can't raise it by n to the power 3 by 2 plus any epsilon. Epsilon is a positive integer. And Chen, Wang and Zi 2 years later settled these conjectures while they were studying higher order differences of logarithm of partition functions for n greater or equal to 45. So this way I can call that Chen factor, because Chen initiated this study. So now we go for higher order analog, that what is called the higher order Turan inequality. So a sequence of real numbers satisfies that higher order Turan inequality if for all n greater or equal to 1 we have this inequality. But this inequality, why this is the higher order analog? So it's, if we see closely, that if it's two factors from the left hand side, that a square of n minus a n minus 1 times a n plus 1, it's already appeared in log concavity, times its one scaling, that means it's a square of n plus 1 minus a n times a n plus 2 minus a n this square factor, which has to be greater or equal to 0. And in 2019, Bilchin proved that this function, partition functions, actually satisfies the higher order Turan inequality for all n greater or equal to 95. And immediately, as Chen style, Bilchin conjectured that again, that it's if I write it down in a different, in equivalent form, the left hand side of the inequality to be replaced by un to be pn minus 1 times pn plus 1 by pn square. Then they said that 1 plus p divided by square root of 24 n to the power 3 by 2 for all n greater or equal to 2. And again 3 by 2 is optimal here. So now we can see that these all inequalities are bounded by two sharp things. Either their lower bound is 1 and upper bound is some 1 plus b go of 1 to the 1 by n to the alpha, where alpha is a fractional number, half integer we can say as of now. So next, the question is, the Larson and Wagner settled, the next question is that from where these all inequalities arises. So now we go to the literature of binary forms. So a binary form of degree d is a homogeneous polynomial of degree d in two variables, x and y. So we write fxy to be sum running from I running from 0 to infinity, d choose I, ai, x to the I, y to the d minus I. So we can choose ai simply, but d choose I, ai is to ease our calculations to get a common factor in terms of some nice sense. For discriminant, calculation of discriminant, calculation of invariant, we can get a suitable common factor. So where for ai are real numbers, but for our context, ai are to be the positive integers, because we are going to replace in a moment that ai to be the partition functions. So now we want to transform the binary form in order to get the literature to let our self entry into the passage of invariant theory. So take any matrix G in GL2C. So if I act G on the two vectors x and y, then the action is given by x to be the linear transformation is actually G11 x1 x bar and G12 y bar, and y to be G21 x bar plus G22 y bar. So we write x and y in terms of new variables with the coefficients in G. And then the binary form transformed into the another binary form, which is f bar of x bar y bar, which is now in the sense that sum I running from 0 to d and d choose I. Now ai bar, the new coefficients pops up, and x to the I and y bar, x bar to the I, and y bar to the d minus I, where ai bar are the coefficients, polynomials. ai bar is actually now the polynomials in ai and entries of G. So now we are ready to define the invariant of binary form. So for any non-negative integer m, a polynomial I that is dependent with in the coefficients a0, a1, an is an invariant of index m of binary form fxy. For any invertible matrix G, then the new transform invariant is just the scalar multiple of the invariant, previous invariant. So now if I choose G to be in this groups SL2C or SL2Z more specifically for our case, then we see that the scalar multiple is just 1. The scalar factor is 1. So now if I in a nutshell what we described for log concavity and log higher Turan inequality, Bill Chain in 2017 studied all these inequalities from invariants of binary forms in his survey paper entitled that SPT functions of Andrews, where he made a lot of conjectures, but what is based on his study is that in the next table we want to show that in the next table this is a binary form for of degree D. So D is 2. If D is 2, then for binary form degree 2 and degree 3, the invariance is actually the discriminant. So for degree 2, a1 square minus a0 a2, if I choose ai to be p of n plus I minus 1, where p is the partition functions, so then this problem is just the positivity of the invariant is just the log concavity for m greater or equal to 26 settled by DeSalvo and Park. For degree 3, it's higher order Turan inequality, which was settled by Chen, Jia, and Wang. And for degree 4, it was conjectured that by Bill Chen that it would be hold for n greater or equal to 185. Now, we go for the two conjectures. That first conjecture is that an minus 1 times an plus 3, that invariance is actually positive for all n greater or equal to 185. But as a companion inequality in chain style, the next conjecture, the conjecture 2, is given by 4 times. It's in the next slide, I suppose. Yes, 4 times 1 plus pi square divided by 16 n cube, an times an plus 2, just the opposite thing. So as again 1 by n to the power n cube is optimal here. We can't replace by n to the power 3 plus epsilon. Now the theorem is the Bose now it's a theorem that's both conjecture is true. Both conjectures are true, and then we are trying to now give a brief sketch of the proof, how one can prove this conjecture. So first we want to estimate that we want to use the main ingredient is the Chen's lemma that by Chen, Jia, and Wang in 2019 in their paper, that they obtained that Pn is bounded between these two nice factors B1n and B2n for all n greater equal to 1000 and 206 from large point on. Before that it won't hold always. So what is the difference between B1n and B2n? If you look closely, that B1n and B2n is different by only the last factor. It's minus 1 by mu n to the 10 and plus 1 by mu n to the 10. But 10 is not any surprising number here. 10 is just they taken for their calculations so as to ease their calculation. So we keep the 10 for our proof, but one can replace 10 by any positive integer for their problem. And it appears if I choose in the Rademacher's formula, if you recall the Rademacher's formula, n equal to capital N equal to 2, the yes yes, for n equal to yes, here for if I choose the capital N equal to 2, then from here we can get this type of inequality, that Pn is bounded by some e power mu n divided by some mu n square times 1 minus 1 by mu n plus 1 by mu n to the k. Very easy. But one has to get the concrete things from there. Otherwise, one couldn't make the inequality stuff from which point on these inequalities hold explicitly. So now we again go back to our proof sketch. Then yes, so yes, now the next thing we need that un to be defined to be Pn plus 1 times Pn minus 1 by Pn square. For convenience, we wrote that x to be mu of n minus 1. Mu n is just pi by 6 square root of 24n minus 1, and y to be mu n and z to be mu n plus 1. And then we define fn and gn, these two quantities. We note that in these two quantities exponential factor still pops up, and there is another factor is that y, x, y, and z, and x, y, and z are, when we write explicitly, then these are the expressions of the form 1 plus fn to the power any rational number. So I will try to give a brief overview on that, how one could estimate all these things. So now fn and gn, then Chen's obtained that this theorem that un is bounded by fn and gn, and for all n greater or equal to 1000 and 207. So now here we go to the next slide. So we rewrite the conjecture in the two following equivalent forms. So we write the conjecture that 4 plus pi square, we put 4 into the scalar factor, that 4 plus pi square by 4n cube minus 3 times this un plus 1 times pn plus 2, and which has to be greater than pn minus 1 times pn plus 3. We just throw these two in the previous two lemmas and previous lemmas and theorems so as to get what we have to prove. So we want to prove the left hand side by its lower bound, and we want to improve the right hand side by its upper bound. So now, in order to get this inequality, we have to prove that how smooth and how we can do the better and better message to get to incorporate the inequality in a nice form. So nice form, I will explain what is a nice form means mathematically. So we have to prove now this inequality, that b1n and b2n, I transform the inequality in terms of classical functions, exponential functions, fractional binomial expansions, and all that. So now, in order to prove this, we will encounter with two main things. That one is the exponential functions in the next slide, and another is the fractional binomial expansion. So we have to estimate the tail of the Taylor series. Actually, we have to want to bound. So for exponential functions, there are two subclasses. If I take e to the power fn with a decreasing sequence of positive real numbers, for fn is some from n naught, from n running from n naught, it's fn is decreasing with limit n tends to infinity, fn is 0. Then one can bound that e to the power fn. In the next slide, we can see that this bound, that the lower bound is trivial, because for fn is a positive integer, we can bound e to the power fn by truncate up to m2, any m2 positive integer, so as to you have to do a ansatz, you have to make an ansatz for which m2 it will work. But for the upper bound, you have to take the ansatz for m1 and you have to truncate up to m1 minus 1th term, and for m1th term we have to found a positive real number a such that this inequality holds in order to be suitably proof for the inequality 3. But for e to the power minus fn, the same situation, fn is a positive decreasing sequence with limit n tends to infinity, fn is 0. Then we have to do a similar thing in our basic from our basic real analysis, that e to the power minus fn, we can bound it by in the next slide we can show that e to the power minus fn is bounded by this factor, that some k running from, we have to truncate up to m4, where m4 is a positive integer, because we pair up the rest of the things into two tuples, of which tuples are positive. And for the lower bound m3, we have to bound it by an odd positive integer, so that each remainder tuples, if if we break the remainder thing into two tuples, each of the factor, and they all are positive. So we can bound this in this way, and then binomial expansion, the last thing we encounter to prove this inequality, that binomial expansion with fractional coefficients, that is alpha is in real numbers, for k is a positive integer, then alpha choose k is nothing but alpha falling factorial k, we say this is a falling factorial k divided by k factorial, that's alpha times alpha minus 1 times alpha minus k plus 1. So in our context, alpha to be a rational number, and alpha to be a rational number, and then we estimate that 1 plus x to the alpha in the next slide, that 1 plus x to the alpha is some k running from 0 to infinity, alpha binomial coefficient k, not binomial, fractional binomial coefficient k, x to the k. So here x, we can regard it in our context x to be a function, you can consider it's gn, something n greater or equal to n1 with limit 0 as n tends to infinity. And similar estimation as we have done for e to the power fn and e to the power minus fn, the estimate this is the end of the estimation, we can do the similar stuff. So after all these estimations, we reach from this inequality to the following inequality of the form, for some functions f, which is in the function of 1 divided by square root of n, which starts from I0, from some positive integer, to L some positive integer, where Ci times 1 divided by square root of n to the I, which has to be greater than 0. So now we note that in all these problems we transform in such a way so that Ci0 is a positive real number, and I is a positive for in our context I equals Ci0, I0 would be some constant, and I to be the 7, that I0 is the 7, actually it's starting from 1 by square root of n to the 7. So if you see, if we have an L equal to 330, it's a quite long term. So if I see that something starting from 1, some constant times 1 divided by n to the power 7 by 2 minus something or plus something, this is always greater than 0. So this is actually the how one could prove all these inequalities to truncate it in such a way so that the first term, after resolving all these inequalities, employing all these estimations, the first term has to be positive and times 1 divided by n to the power some alpha is a half integer. That's how one can estimate in this way. So now I am now quite in the end of my talk. So what is the possible deduction? In email correspondence, Professor Bilchen said that I didn't know any reason why they should be valid for the partition function for large n. So these questions struck me at most, although I know how to prove it, but he wants to know that why they should be valid. Because Bilchen observed up to degree 4 binary form that positivity of invariance with such coefficients holds good. But what for the higher degree binary form? So for degree 5 binary form, in the next slide, yes, for degree 5 binary form, to investigate these questions, we went to the degree 5, and one of the most simplest invariant for the degree of 5 binary form is given, that up to sign. That sign means which if I is a binary invariant for a binary form, then minus I is also an invariant. So we now go to the next thing, that I to be this invariant, and it is the most simplest. I didn't believe at all that it is the most simplest. And then if I replace that I to be a0, a1, a5 to p of n minus 1 to p of n plus 4, and then we checked in Mathematica that for all n up to 50,000, that for all n greater or equal to 348, which will be shown in the next slide, it's negative. Yes. So discriminant is made up of invariants for binary forms. Binary forms are for binary forms, discriminants are made up of the invariants. So if I take degree 4 binary form, then it's 256 times 2 binary forms sum a cube minus 27b squared. So we already know that due to the result, well-known result of Griffin, Ono, Rowland, and Zagier, they prove that partition functions, actually the Jensen polynomials associated to partition functions, is always hyperbolic. That means they always have real roots. That means their discriminant is positive. But one can't comment on that how these invariants are always, why these invariants are always positive, although discriminant is positive. So the question is now, the last, I want to pose this question, that this is from algebraic side, that is there any connection between the sign of invariants where the coefficients are taken from partition functions and the positivity of the discriminant for binary forms with such coefficients? Thank you. Thank you for coming to my talk.
Thank you, Mr. Kostov, for the very nice talk.
Thank you.
So, are there any questions or comments?
Yeah, I have. I have. Hey, Kostov, Rajat here. So my question is that is there any similar result for log concavity for over partitions? Like
yes, recently in Ramanujan journal, I couldn't recall the name of two Chinese people. I saw that over partitions, log concavity and results is known.
Oh, similar
but for the log concavity.
Yeah.
Yes.
Just, no. Speak, please.
Okay, for the log concavity, one can see that log concavity for higher order Turian everything is there, but you can ask for this type of, for invariance there are no inequalities as I have known till now.
Okay.
I do not know. I am still I still can't say you quite confirmly, but you can see in the paper in Ramanujan journal that invariant thing they didn't do because it's not been done in partitions at least.
Okay.
For over partitions they didn't do it.
Thank you for the wonderful talk. Thank you.
Thank you.
Yeah, are there any more questions? Yeah, if no, let us thank Mr. Kostov for the nice talk.
Thank you.
And the next speaker is Mr. Subhash. So, Subhash Chand, are you here? Subhash.
Subhash, yes.
Yeah.
Yes, please share your.
Subhash, can you please share?
Am I audible?
Unmute your.
Yes. Yes, I unmute. Am I audible?
No, your voice is breaking. So you unmute your microphone and share your slides.
So now is it?
No, still it is breaking. But first you can share your slides. First share your slides.
Okay, share my slides.
Go to present now, and then present entire screen, and then no, you can't see your slides.
So Subhash, can you present your
Actually, I don't know what.
No, go to present now.
Yes,
Go to
yes.
present now.
yeah?
Go to present.
And
Then what do you see?
Sir, you lost.
Go to present now. I think there is some network issue. So
yes, your voice is also breaking actually.
okay, so maybe I don't know. First, can you rejoin? You leave the meeting and rejoin. Okay, then we'll see whether it's working or not. His network is, I think, not good. There is some network issue.
Yeah, sometimes this kind of problem.
Let him join. Otherwise, you can go with next candidate.
Yeah, let us see.
I think Rajat is ready, right? Rajat.
Yeah. I'm ready.
Let's see if Suhas, if there is a problem with Suhas, then we can go with you.
Sure.
Rajat.
Yeah, so
Sure, Professor.
So let him join. I think you can go ahead with Rajat.
Rajat, yeah,
Yes, Professor.
Suhas has
yeah, I
joined.
think Subhas has joined.
Yes.
So Suhas, can you try one more time? Then let's see. Just first unmute yourself and then go to present now and share your screen.
Yes.
Yes. Great. But, now open your slide. Open your slide. Open your slides. And hello, Subhas. I think we have lost.
I think
Yeah, you can.
we can
Yeah.
continue,
Yes.
and then maybe yeah.
Yes. You will see later.
So should I continue with Rajat?
Yes. Sure. Go ahead, please.
Then you can talk to him and fix the timing later. Huh? Okay, so Rajat, can you please share your screen and slides?
Sure. Let me share. So tell me if my slides are visible. Slide is visible.
Yeah, now it is visible. So, so should I start?
Yeah.
Go ahead.
Okay, so welcome to the next lecture of the evening session, and the speaker is Dr. Rajat Gupta from IIT Gandhinagar, and he will be talking on sum of tails identities. Yeah, Rajat, over to you.
Yeah. Thank you, Professor. By the way, I am not graduated yet, so
Oh,
it's Mr. No, it's okay. It's okay. So first, I want to thank the organizers to let me in for this talk and presenting my work in this conference. So today I'll be talking on sum of tail identities, which is I wrote a paper on it, and I have submitted this for publication in this year. So let me start with the notation first. So let me define the q shifted factorials. Like a sub 0 is equal to like a base of a with base q sub 0 equal to 1, and similar for n index is like the product over 1 minus aq 1 minus aq to the n minus 1 for n greater than or equal to 1. And suppose if you wanted for a sub infinity, then you have to take an extra condition mod q less than 1 due to the convergence of the infinite product, which we defined like aq sub infinity. Okay, so we'll throughout the talk we'll be continuously using these notations, and then we'll define the Gaussian coefficients for n and k, where are integers. It's like n of nk, and it's just an analog of q shifted analog of binomial coefficients. So it's like nk is equal to q sub n upon q sub n minus k, and qk for k less than or equal to n and 0, otherwise it will be 0. So let me start with the identity of Ramanujan, because he was the first one who start with this, who start with the sum of tail identity. So what do you mean by sum of tail? Means you are summing the tail. Suppose you have an an as a sequence, and you have the limit the limit of an is a, then you are summing an minus a. That means you are summing the tail. Okay, so let me go over the first Ramanujan identity, which is this. Now he is summing the tail of minus q sub infinity. That means infinite product of 1 plus q, 1 plus q square, 1 plus q, 1 plus q cube up to infinity. So he obtained the right hand side, which involves the generating function of divisor function, which is summation over qn upon 1 minus qn, and the Ramanujan sum, which is on the extreme right. It's qn plus 1 by 2 1 minus qq sub n. We'll discuss more on this in the later of the talk. So in the sequel in 2001, Don Zaghi actually derived this identity for qq sub infinity. That means he was summing the tail of qq sub infinity, in which he also got the representation of divisor function and this summation. In this sequel, recently in the same year 2001, Professor George Andrews, Uroz, and Ono obtained this more general sum of tail identity, which involves the tail of t infinity upon a infinity, which involves this summation. And as you can see, it's a little bit complicated, but it's really useful. And after 4 years, Professor George Andrews and Pedro Freitas actually give a different representation of the left hand side. So what does it mean? It means that they both use the different methods to solve this. So let me be explicit that the first equation actually done by differentiating the q products. Okay, and in the second theorem was actually done by using the Abel's theorem. Okay, so in the talk we'll be using the differentiation over q products. So let me first give the motivation of this project, where it arose. So if you see the paper of Professor Dixit and Ayumi and Professor Maji and Professor Sood, in their paper they obtained this identity, which is also a sum of tail identity, and it's a finite analog of a very well known identity, which is this. So the question was to generalize the first identity. Okay, so it means how can we generalize that, and we successfully answer that in the main theorem. The next main theorem which I gave is, suppose you have a gx which is sum over gn x to the n, which is convergent for mod q less than 1 and mod t less than 1 and mod x less than 1, and a belongs to c. Then we have this. Look, then we have this theorem. So to make it simple, that to make it look that from where we get the previous identity as a special case, let me more specialize it. So we got this identity as a special case, which is this. And if you put c equal to -1, so you will get the previous, so you will get the proposed generalization which we want. And if you take n tends to infinity, so you will see that we got the result of Andrews, Garvan, and Liang. As you can see, if you take n tends to infinity, so this q binomial coefficient, like capital N by n, converges to 1 upon qn. So you get the cancellation over qn's on both sides, and you will get the identity. And we will discuss more on this, because our second main theorem will be dependent on the last identity. So let's discuss about the Ramanujan sum, which we have seen in the first slide. So Ramanujan summation is represented like this: sigma q is equal to qnn plus 1 by 2 upon minus qq sub n. It has a really interesting properties, and in his own words, Ramanujan wrote that sigma q, if we represent it as Sn of q to the n, and we expand that series, you will see that the coefficients up to q to the power 3288, they all are between -8 and 8. They all are between -8 and 8. So by seeing this, Professor Andrews actually conjectured two problems, like lim sup of Sn equal to plus infinity, because you can see that like up to 3000, up to the power of 3288, the all coefficients are between plus and -8, and still you have lim sup of Sn is equal to plus infinity, as well as Sn equal to 0 for infinitely many integers. And he actually himself actually settled these two conjectures. So let me go over the finite analog of this, which is the theme of the next theorems. So let me define sigma nq is equal to the binomial coefficient qn q to the nn plus 1 by 2 upon minus qqn. So as you can see, if you take n tends to infinity, then n over n will leads to qn, and that will cancel out with the numerator. Okay, so we got the representation for sigma qn, which is this, and if you take n tends to infinity, so you'll get the new representation for sigma q, which to the best of our knowledge is new and that nowhere present in the literature, but however it's a special case of Heinz-2-Phi-1 transformation. You have to play with the coefficients in the Heinz-2-Phi-1 transformation to get that, and the representation is this, like sigma q is equal to q infinity plus 2 summation over qn upon 1 plus q to the n qn plus 1 qn plus 1 infinity. Like most of the authors who work in this area, like like they are more interested in the combinatorial interpretation of some of the partition identities. So let me give the combinatorial interpretation of this. So for that, let's first define the dn. So dn denote the number of partition of n into distinct parts, and bn is denote the number of partition of n in which the only smallest part allowed to repeat. That means suppose you have a 5 plus 5 plus 6 plus 6, so that partition won't be counted in bn. So the partition like 5 plus 5 and then 6 plus 7, so only smallest part is allowed to repeat, no other part. And the hash pi is denotes the number of parts in a partition. Like suppose you have 5 plus 3 plus 2, so 3 parts, so hash of pi is 3 for that partition. And the rank of pi, so the rank of pi was introduced by the famous theoretical physicist Freeman Dyson. So the rank of pi is just for any partition, took any partition and just subtract the largest part minus the number of parts. So that is what he called rank of a partition. So relating to that, we obtain this combinatorial interpretation, which is summing over the partition belong to this class dn, which we have defined above, is equal to the weight is -1 to the number of parts minus -1 to the rank of pi is equal to 2 summation over this class bn, which the weight is -1 to the number of parts. Okay, so let me go to the another different representation of sigma q, which is this. So if you see closely, you can see that this is very much similar to the identity which I've shown in the first slide of Ramanujan, right? Here the only difference was in the second summation in the small bracket, which is 1 over 2 minus summation n goes to 1 to infinity qn upon 1 minus qn. Okay, so the only difference was that. And similar, and for the previous case, we also obtained the combinatorially interpret this identity. So dn and bn are same in the defined in the previous slide, and small dn is a number of partition of n into distinct parts, and defines sigma prime 0 is equal to half, and for k greater than or equal to n, sigma prime k is equal to summation d divides k, summation over d divides k minus 1 to the d minus 1. Then we have this combinatorial interpretation. Okay, so now let me go to the second main theorem of this talk. So let me first motivate you that how we got that thing. Okay, so the work so let me cite the work of Andrews, Garwin and Liang, in which he obtained a sum of tail identity which actually related with the crank of a partition. So as a previous case, the rank was defined by Freeman Dyson. The crank was also defined by Freeman Dyson. Oh, sorry, the crank was defined by Professor Andrews and Garwin. And the definition of crank is, suppose you have a partition lambda, then L pi denotes the largest part, omega of lambda denote the number of ones in that partition. Suppose 1 plus 1 plus 1 plus 3 plus 3. So how many ones in the partition? 3. And mu of lambda denote the number of parts of lambda larger than omega lambda. Okay, and then the crank will be defined like this. If omega lambda is equal to 0, that means if the number of ones in a partition is 0, then the crank is only the largest part of that partition. If omega lambda is greater than 0, then the crank will be the difference of mu lambda minus omega lambda. So we successfully generalize this identity. So here it is. So for beta belongs to C and alpha and mod Q less than 1, this is the identity. And if you put beta equal to Q and alpha equal to Q, you will get the identity of Professor Andrews. Now, what's the interesting thing is that in the right side, you have the what do you call? Oh, let me go. So in the right hand side, you have the generalization of the half Lorentz sum, which is in the extreme right, and this is the universal Mach theta function, the derivative of the universal Mach theta function. So what's the universal Mach theta function? Universal Mach theta function just defined like b to the n qn square upon bq sub n qn, no n. That means we are differentiating that. So we got the relation between these two. So let me first define what are the half Lorentz sum. So half Lorentz sum was first defined by X Zeong in his paper, which I cited it here. So it's for mod q less than 1, h of q is minus 1 to the n qn plus 1 by 2 upon 1 minus qn. So as a special case, now you have so many parameters like alpha and beta, so you can play with it. So as a corollary of this, we got this identity, and we got like differentiating with respect to alpha, you will have this identity. For beta belongs to C, mod q less than 1, you have this identity. That identity was actually given by Ramanujan in his volume 2, in his notebook, which is published by TIFR in volume 2. And the special case beta equal to 1 was actually rediscovered by Andrew, Chan and Kim in this paper, the cited paper. So let me give some corollaries related to these and with the sum of tail identities. So the first corollary is this: summation n 0 to infinity. You are now summing the difference of two infinite products of minus qn plus 1 q sub infinity minus qn plus 1 q sub infinity is equal to in the form of this half Lorentz sum. And the second corollary is this, which you are summing over these two infinite products, and you got these two representations. Okay, so let me the final main theorem of this talk will be on the FFW function. So it's a short form, which was the short form of the function defined by Focking and Wang. So he showed that if Dn is the collection of partition of n into distinct parts, and S pi denote the smallest part in a partition of pi, then they satisfy this relation, where Dn denotes the number of divisor of n, and it was way much studied by so many authors. So we also studied this, and we also find a one parameter generalization of this, and due to that we got an interesting theorem. And as a special case, we got the generating function of SPT function. So we'll see in the next few slides. So recently, Andrews, Garvan, and Liang actually generalized in a different setting this function by a parameter C, and he obtained this identity. As you can see, this identity is also a special case of our main theorem, which I showed just few slides back. So this is the generalization of Andrews, Garvan, and Liang of the FFW identity. So let me go over the generalization of one parameter by us. So here we go, another generalization of FFW function by a parameter C. And now the weight will be minus c to the number of parts, smallest part. Okay, now before the weight was minus 1 to the number of parts into the smallest part. Now here it is minus c to the power of number of parts into the smallest part, where c belongs to c. So we got this function, and you can note that if you put c equal to, and you will easily get back to that result. Now the theorem involving this coefficients is this: that the generating function of FFCW function is this, the middle one, the term in the middle. So it's summation n equal to 1 to infinity minus c to the n qn plus 1 by 2 upon qn 1 minus qn. In the case of Andrews, he got the c in the place of in the place of 1, where 1 minus cq to the n. Okay, in the just beside to the q to the n in the denominator. But now here we have minus c in the above in the numerator. So we obtained this identity. Now, so let me give the proof of it, because it involves both methods, analytic and combinatorial method also. So first let me see let me take the case c tends to 1. What happened on that case? So FFW function. So if you take c tends to 1, you will obtain this identity, which is a special case of the last one. Okay. So let me sketch the proof. So you have the generating function of FFWC. So you can write this identity as summation n goes to 0 to infinity, the coefficient with the q to the n. And then if you combinatorially interpret that, you will get that minus c summation n goes to 1 to infinity n q to the n c q to the n plus 1 infinity. So in the last summation, you can see that if we suppose n is the smallest part, So you can see n in the multiplication, right? So that is why here s pi is coming in the multiplication in the middle. Okay, and where the minus c to the number of parts are coming, so minus c is in the out of the summation, and the other c are coming from the infinite product, which involves in c cubed the n plus 1 infinity. Okay, so it's not hard to see, but it is visible from here. Then we apply, within in the second step, we use this identity of Euler, which is x infinity is equal to this. Then we can use in the second step, and will lead to this, and we just interchange the summation and use the differentiation of the geometric series, okay, with z equal to q to the m plus 1. So you will get the second step here. Now what we have done is that we take 1 minus q to the m plus 1 from square to the inside of qm in the denominator, okay, and then we shift the summation from 0 to infinity to 1 to infinity. Then we get the first equality of the theorem. Now to prove the second equality of the theorem, we have to work a little bit. So let's rewrite this identity in a different form. So as everybody know that like a sub q of n, and if we divide it by a to the n, I take a tends to infinity, that will lead to q to the mm plus 1 by 2. That is what we had done here, okay. And zn upon zqn, if you see, if you take zn upon zqn, it nothing but 1 upon 1 minus zqn. That's why if you take z equal to 1, you will get 1 minus q to the m. And if you take, oh sorry, I just misplaced the index. So here it is summation running over m, but here inside I written over m, sorry for that. So consider it the n in the place of m in the place of n. So take t tends to 0 and then differentiate this series and take z equal to 1. Now use the Heinz transform with a equal to q, c equal to cq, and t equal to z, and b replaced with t. Then you will have this identity. Now just simplify it and play with the variables. You will get to the third, then you get to the last stage. Now in the to end the proof, we'll apply the Fine's identity, which is this. And if you apply this identity and you take the differentiation, after the differentiation, if you took z equal to 1, you will easily get that. So we are different, as I mentioned it earlier, this term will be, the proof of this will be dependent on the differentiation of infinite products, q infinite products. So from there we are getting these Lambert series. So hence we got the second equality. And now we have the parameter c, so we can play with this. So in the previous case we had first and c tends to 1. Now what we do is that we first differentiate this identity with respect to c, and then take c tends to 1, and then divide both sides by q infinity to get a simple result. So we surprisingly get the generating function of SPT function. So what the SPT function is? SPT function is just counting the smallest part in a partition. Suppose you have a partition like 1 plus 1 plus 3 plus 4 plus 5. So how many parts are smallest? So 1 is the smallest part. How many times is it coming? 2. So SPT of that number, the number which you are partitioning, is 2. So this is what we got as a corollary, which was really surprising for us, that after differentiating and taking the limit, we got this thing identity. So this is the generating, the middle equality will be the generating function of the SPTN, and we got this corollary as a special case. So with that, I'll end my talk, and thank you for listening. Thank you.
Okay, thank you very much, Mr. Rajat, for the nice talk. So are there any questions or comments? If there are no questions, so let us thank Mr. Rajat for the talk.
Thank you, sir. Thank you.
And the next speaker is Mr. Rahul Kumar. And so Rahul, are you ready?
Yes, sir.
Yeah, so can you share your screen? And
Sure.
Rahul, share your screen. Present and share your screen.
Yes. Give me 1 minute. Yeah.
yes.
Yeah. So is it visible?
Yes, fine.
Yeah. Okay.
So should I start, Rahul?
Yeah. Yes, sir. Sure.
Okay, so the next lecture is by Rahul Kumar, Mr. Rahul Kumar from IIT Gandhinagar. So he will be talking on superimposing theta structure on a generalized modular relation. Yeah, Mr. Rahul, please continue.
Thank you, sir, for the introduction. So first of all, I would like to thank organizers of this conference for giving me this opportunity to speak here. So I will talk today about this superimposing theta structure on a generalized modular relation. This is joint work with Professor Atul Dixit. So this is how my talk will go. So first we will discuss about modular relations and why the study of these modular relations are important in the theory of analytic numbers. And then we will discuss our work on these modular relations and then this new special function, generalized Hurwitz-Zeta function and its theory. So let's start with the definition of Hurwitz-Zeta function. As we know that Riemann-Zeta function is defined by this infinite series in this right-up plane where part of x greater than 1, where it is an analytic function. Moreover, that it can be analytically continued to the entire complex plane except for the simple pole at h equal to 1, and it can be done by the following functional equation, which was given by Riemann himself. The functional equation is giving you relation between zeta values of s at s and at 1 minus s. So for the further discussions, let me define these two functions known as Riemann-Zeta function and Riemann-C function. Riemann-Zeta function is actually nothing but this left-hand side of this functional equation with these two correction factors, and Riemann-C function is defined in terms of this Riemann-Zeta function. So because of these two correction factors, Riemann-Zeta function is an entire function of s, and it can be easily observed that Riemann-C function is an even function of t, and it is a real function for real t. So let me discuss one important paper of Ramanujan titled as New Expressions for Riemann's functions, Riemann-Zeta function and Riemann-C function. In this paper, Ramanujan considered two types of integral, and first one has this following form where you have this f which has to be of this form, f of phi of it and phi of minus it, and you have this Riemann-C function in its integrand. Because of the evenness of this cosine function, one can see that if you replace alpha by 1 by alpha here, this integral will be an invariant under this map, right, because of this cosine function. So that means this integral will generate transformations of the form f of alpha equal to phi beta, right? So beta is just 1 by alpha. So and Ramanujan also given the one explicit example of this fact. So in this identity you can see that alpha is just going to beta. And this is the integral which involves this Riemann-C function and which is generating this transformation formula. So if you prove this identity to this last one, then you will get this identity, middle one identity, like for free. If you then why? If you replace in this identity alpha by beta, you will get this identity very easily, right? So there are few examples in mathematics where you have these kind of transformation, right? This alpha is just going to beta. And in the last section of his paper, Ramanujan considered more general integral. Now you have these two Riemann-C functions and different arguments. And if you see the general form of this integral, that will be of this form. So now f will take of the form of this form, phi of z it and phi of z minus it, where phi must be an analytic function of both the variables. So again, because of the invariance of this cosine function, these integrals now generate the transformation formula of the form f of z alpha equal to f of z beta, where z remains same but alpha goes to beta. So one may wonder why Ramanujan suddenly considered the study of these integrals involving this Riemann-C function. So for that, let me quote Hardy, what Hardy said about these integrals. So about the first integral, which Ramanujan considered in his paper, Hardy said that this integral has properties similar to those of the integral by means of which I proved recently that Riemann-Zeta function has infinitely many zeros on the line real part of is equal to half and may be used for the same purpose. So I will talk more about this Hardy's theorem, but we know that this was the first big result in the direction of Riemann hypothesis. And about the last integral, Hardy said that this integral, the properties of this integral resemble those of one which Mr. Littlewood and I have used in a paper to be published shortly in Acta Mathematica to prove the second movement of the Riemann-Zeta function. And we know that these type of problems are very important in the analytic number theory. So by these two quotes, one may convinced that the study of these integrals is very important. And I will give more non-trivial examples of these model relations and the integrals involving this Riemann-C function. So in this talk, I will be mostly talking about these integrals involving Riemann-C function. So now let me give you one beautiful model relation from the Ramanujan's lost notebook. So what Ramanujan is doing here, he is considering this digamma function, which is nothing but a logarithmic derivative of gamma function. What he is doing, he is actually subtracting the first two terms from the asymptotic expansion of psi x. So if you take asymptotic expansion of psi x as x tends to infinity, you will see that you have these two terms on the in its asymptotic. And what he is doing then, he is actually considering the series of this lambda function, and he's getting this model, beautiful model relation, where you can again observe that alpha is just going to beta everywhere, and this is the integral which is generating this model relation. So now let me give you the definition. What do we mean by this modular relation? So as we know that modular forms are function which transform nicely on this upper half plane under these two maps, inversion map and translation map. On the other hand, by a modular relation, we will be meaning that it will be translated under this map inversion, but not necessarily by this translation. Okay, so and this inversion map can be recasted in this form: alpha going to beta, and where alpha beta equal to 1, and real parts of this alpha and beta are greater than 0. And we have seen the examples of this form, this Ramanujan's two aforementioned transformation of this form, right? F of alpha equal to f of beta. So now let me give the definition. What do we mean by generalized model relation also? So that generalized model relation will have one more parameter besides this alpha. Okay, so now let me give you one example of generalized model relation also, which was proved by Dixit in 2011. What he did here, again, he take this zeta function and again subtracted these two terms from its asymptotic expansion and studied the same integral which was studied by Ramanujan, but Ramanujan did not give this transformation formula, which is of the form f of z alpha equal to f of z beta. So you can see that alpha just going to beta and z remains same. Everywhere this is the case in this formula. Okay. So now let me give you one non-trivial application of these integrals in the theory of analytic number theory. So this integral was considered by Ramanujan. If you take here this f equivalently to 1, then you can evaluate this integral equal to this evaluation infinite series. Okay. And by Fourier inversion, you can see that this Riemann-Stieltjes function will have this integral representation. Okay, and for the convenience, if you define one function h naught t in terms of this Riemann-Stieltjes function, then the last previous equality will have this form. H naught t will be equal to this integral, where this phi u is an infinite series. Okay. So what then Bruin did, he actually considered more general integrals. Besides h naught t, he introduced this exponential function here. So you can see if you take a v equal to 0, you will get back to this h naught t. And then Polya proved that v has purely real zeros for some v, then hv prime has purely real zeros for all v prime greater than v. And then what Bruin showed that zeros of hv are purely real for v greater than or equal to half. And we know that Riemann hypothesis is equivalent to the statement saying that all zeros of h naught t are real. What is h naught? H naught is this Riemann-Stieltjes function. It is well-known fact that having real zeros of Riemann-Stieltjes function is equivalent to the proving the Riemann hypothesis. Okay, and then what Newman showed, that he proved that there exists a lambda with this property that then hv has purely real zeros if and only if v is greater than or equal to lambda. And now if you see these two statements, you can observe that Riemann hypothesis holds provided lambda is less than or equal to 0. Why? Because we have to take h naught t, right? So, but recently what Rogers and Tau showed, they proved that lambda has to be greater than or equal to 0. So now by these two statements, you can see that if Riemann hypothesis is true, it has lambda has to be 0 only. There is no choice for lambda. So that's why Rogers and Tau mentioned in their paper that if Riemann hypothesis is true, it is barely so. So from this example, you can see that these integrals involving Riemann-Stieltjes functions has very non-trivial applications in the theory of analytic number theory. Okay, so I will give one more non-trivial application of these modular relations and these integrals. So this is the well-known theta transformation formula, and this is one integral evaluation for this theta transformation formula, and this is the identity which Hardy used to prove his theorem about infinitude of zeros of Riemann-Zeta function on the critical line. So you can again see that the non-trivial application of this integral Riemann-Stieltjes function. And moving further, let me give you the one generalization of this transformation formula, which is known as generalized theta transformation formula. Now you can see here alpha is going to beta, but now W is going to IW. So this formula has of the form f of W alpha equal to f of IW beta. So if you take W equal to 0, you will get back to the theta transformation formula. But up to 2013, there was no integral evaluation known for this theta transformation formula that was given by Professor Dixit, and he given this integral representation where this nebula function is nothing but a combination of these 1f1 functions, which are the confluent hypergeometry function, which are known, so well-known function, entire functions. So by these some examples of non-trivial applications, we are motivated to study some further integrals involving this Riemann-Roch function. Okay, so what is our goal of this talk or our this work was that for that let me define this definition of what do I mean by theta structure that I have term in my title of my talk. So a modular relation with the theta structure is the one in which associated function, this f of W alpha, becomes invariant when you simultaneously replace W by IW and alpha by beta. Okay, and we have seen already such an example that the general theta transform formula here, that alpha is just going to beta and W goes to IW. So we say this type of transformation formula that modular relation with the theta